ठीक ठाक। मैंने सुना है, मुझे यहाँ आने के लिए ना मेरे पास गाड़ी नहीं है, तो लिफ्ट नहीं मिल रही थी, तो मैं
Good evening, ladies and gentlemen. Please be seated. We'll be starting our session soon. Bismillahirrahmanirrahim. I welcome you all on behalf of the Organizing Committee on 43rd Annual Conference of Pakistan Association of Pathology. I am Sadra Arshad, and along with me, Dr. Khurram Minhas will be moderating this session. We'll start our day with the recitation of Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الرحمن علم القرآن خلق الإنسان علمه البيان الشمس والقمر بحسبان والنجم والشجر يسجدان والسماء رفعها ووضع الميزان ألا تطغوا في الميزان وأقيموا الوزن بالقسط ولا تخسروا الميزان والأرض وضعها للأنام فيها فاكهة والنخل ذات الأكمام والحب ذو العصف والريحان فبأي آلاء ربكما تكذبان صدق الله العظيم.
Jazakallah. I request you all to please stand for the national anthem.
I would now request Dr. Shahid Parvez, the President of PAP and Chair Organizing Committee, to come on the podium and continue with the welcome address. Thank you.
Professor Ataur Rahman, FRS Chief Guest, office bearers and organizers of Pakistan Association of Pathologists and all societies of pathology, foreign delegates, sponsors, pathology colleagues, trainees, support staff, Assalamu alaikum. It's my proud privilege and pleasure to welcome all participants of 43rd Annual Congress of Pakistan Association of Pathologists and 8th Joint Conference of Societies of Pathology at the largest port city of Pakistan, that is Karachi. It was way back in 1976 when a handful of pathologists, only 18 in number, gathered in a small room at Jinnah Postgraduate Medical Center, JPMC, Karachi, and created this national forum for the pathologists of Pakistan. Late Professor Naeem Jafri was elected as the founder president, and late Dr. Mansoor Dar as founder secretary treasurer at that time. First annual conference of the PAP was held in 1977, and since then PAP holds its annual congress in every year in one major city of Pakistan. Only inevitable gap came during the COVID-19 period, and here we are back after 2 years. With time, as pathology discipline evolved, a need was felt to have academic platforms of major subspecialties of pathology like chemical pathology, hematology, histopathology, microbiology, immunology, and most recently, molecular pathology. Most office bearers and members of organizing committee of these societies are sitting here, and I extend my sincere gratitude for their hard work putting together such an attractive and comprehensive program. It is so heartening to see active participation by pathologists at various stages of their career to join from across nation and from abroad. I am particularly indebted to our foreign speakers who are able to join both in person and virtually. It is unprecedented that next 2 days, 6 parallel sessions of these societies will be held over and above several pre- and post-conference workshops which are continuing since yesterday by all societies. This year, PAP also extended over 30 fully funded travel grants to the trainees from across Pakistan, covering their air tickets, stay at this hotel, and registration, along with the several prizes which will come later for the best oral and the poster presentations and the prestigious Bukhari Gold Medal. Finally, let me remind all that PAP is your parent body, which stands tall like a tree, with several branches further differentiating into leaves, flowers, and fruits. However, PAP is the main trunk of this tree, and protecting and looking after this well will be the best guarantee to best serve our discipline, which is the lifeline of the modern medicine. Currently, we have over 650 members of the Pakistan Association of Pathologists, mostly life members. And during this conference alone, we will be awarding 30 life memberships, over 30 life memberships to the new pathologists. And hope this trend goes on, and till the next year PAP, which is tentatively scheduled in Lahore from November 17 to 19. At the end, I dedicate this academic event to all who so carefully looked after and nurtured this common platform of pathology for over 2 decades, for over 4 decades, enabling me to stand on the shoulders of these giants to say you a very good evening. Thank you.
Thank you, Dr. Shai Pervez. I would now request Dr. Adnan Zubairi to come on over the podium, and he's the Secretary of Organizing Committee. Thank you very much, Dr. Adnan.
Bismillahirrahmanirrahim. Good evening, distinguished guests, speakers, members of Pakistan Association of Pathologists, and all societies, friends, sponsors, and the colleagues from the clinical laboratories. A very warm welcome to 43rd Annual Conference of Pakistan Association of Pathologists and 8th Joint International Conference of Societies of Pathology and CAMCON 22. I am so pleased to see so many colleagues and friends, not only from the Karachi, but from the other parts of the Pakistan as well as abroad. But at the same time, we are missing those colleagues which wanted to come here, but due to their commitments, they couldn't come. These conferences are a good opportunity for the colleagues to meet again and again, and have a good networking. The PAP organizing committee and members of the scientific societies have worked extremely hard to prepare outstanding conference workshops and scientific sessions. We have exceeded the total number of papers ever presented and the total number of people ever registered in PAP conference. The quality of scientific programs is world-class and spectrum of topic is very current and broad. An impressive roster of distinguished speakers from Pakistan and abroad has been assembled for the opening ceremony and the plenary sessions. Organizing committee is committed to provide maximum hospitality. We are here to serve you. Enjoy your participation in the conference and memorable time visiting the exhibition area and the city in these 3 days. Thank you very much.
Thank you, Dr. Tanzobari. I would now request Dr. Shahid Parvez to come once again in order to invite our chief guest for the prestigious Razi lecture.
All right, so a long time ago, in his book, Profiles of the Future, Arthur Clarke cited that modern science and technology will be indistinguishable from magic. Christopher Columbus, an Italian explorer and navigator, is known for his 1492 discovery of the New World of Americas. Of course, there were already people living in Americas. However, they were hostile to these European invaders. However, having significant knowledge of astronomy, Christopher Columbus correctly predicted a total lunar eclipse on March 1, 1504. Jamaicans bowed before him and said, that your God is much superior than ours. This was no less than a magic for them. However, understandably, it was no magic but the power of science. I personally, like you, have a huge respect for these natural philosophers or scientists who have taken us out of the dark ages, as it was only a few centuries ago that even in Europe, witch hunt and similar dogmas were widespread. It taught us the value of reason and logic by simply asking questions, making observations, devise hypotheses, and test them. Just today, irrespective, entire humanity benefit from the fruits of science and technology. Just imagine a world without vaccines and antibiotics. Memory of hundreds and thousands of people who perished due to COVID pandemic is in most recent memory, salvage came from nowhere else but science in the form of, say, vaccines, antibiotics, and so on. Having said that, today we have a scientist with us who really fulfill the comprehensive definition of a true scientist. As a matter of proof, he is among those very few Pakistani scientists who is a fellow of the Royal Society of Science, which is the oldest and most prestigious fellowship of the world. This is awarded throughout history to eminent scientists only, like Isaac Newton in 1672, Michael Faraday in 1824, Charles Darwin in 1839, Ernest Rutherford in 1903, Albert Einstein in 1921, Paul Dirac in 1930, Dorothy Hodgkin in 1947, and Professor Ataur Rahman in 2006. Other from Pakistan include none but Professor Ata's predecessor, Salimuzzaman Siddiqui, and Professor Abdus Salam, but they are not with us. And most recently, the Zulfiqar Bhutta, Professor Zulfiqar Bhutta was in 2020, so in a country of 225 million, so far such prestige has come to very few. Professor Atta was also a federal minister of science and technology in the Musharraf era in the early 2000, I think starting from 2000 to 2002-03. And during that short period of time, we witnessed for the very first time unprecedented budget allocation for higher education, research productivity, and a huge leap in terms of the the value which was given to the science and education. So please welcome Professor Ataur Rahman for the Razi lecture in remembrance for Abu Bakr al-Razi, one of the greatest figures in the history of medicine in the medieval period and Islamic Golden Age. Professor Ataur Rahman.
Thank you very much, sir. Is it possible for me to change slides from here? Thank you. Bismillahirrahmanirrahim. Assalamu alaikum. Dr. Shahid Parvez, Dr. Adnan Zubairi, the pathologists of Pakistan, doctors, students, ladies and gentlemen, Assalamu alaikum. Well, I'm delighted and humbled to be here, very grateful that you have invited me. Let me begin with an apology. I'm not a medical doctor. I'm a professor of organic chemistry and a fairly ancient professor because I did my PhD from Cambridge University back in 1968. So some 54 years ago, or 53 or 54 years ago. So I'm an organic chemist, and that's what I do now in the institute. I'm involved in research and have been involved all my life. I'm going to carry on from the magic that Dr. Shahid, you talked about, the magic of science. And I'll talk to you about the wondrous world of science, where truth is often stranger than fiction. And every day brings 1,000 discoveries, often serendipitously. Scientists trying to do something and achieving, often by accident, the whole field of nanotechnology, for instance, through the discovery of buckyballs, and there are many other examples of that. So let me start with the genomics, a field which is close to many of your hearts because I see there are many lectures in the field of genomics which are going to be delivered during this conference. Two ladies, Jennifer Doudna and Emmanuel Charpentier, they were awarded Nobel Prizes. They shared the Nobel Prize for 2020 for their discovery of a very exciting technique for gene editing. This is a kind of a molecular scissor which consists of an enzyme Cas9 and a guiding RNA, and it slices your DNA at in a particular area, and then you can so the defective genes can be addressed in this manner. So this is now really having a huge impact in the world of science. And this is just yesterday's paper published in Nature Biotechnology, which described how a new variation of this has been developed, which can take very long pieces of the genes present, about 36,000 base pairs, and deliver them into human cells. So it holds promise to treat diseases such as cystic fibrosis and other diseases that are caused by mutations in a large number of genes. So this is finding increasing use in medicine today, this whole field of gene editing. अब आप सोचें ज़रा, just think about it. It takes thousands or tens of thousands of years for new species to evolve. Here you can create new species in a matter of weeks just through gene editing techniques. So it really is a huge revolution that has come in. And if you want to see this in action, you may want to visit my center, the International Center of Chemical and Biological Sciences at Karachi University. And I have established a center in my father's name, the Jamilur Rahman Center for Genomics Research, which has state-of-the-art gene sequencing facilities. And a lot of very exciting work is going on there on gene editing. Again, this is finding application in personalized medicine. And this is again a paper published earlier this month on the use of CRISPR engineered genes for immunotherapy. So immunotherapy is a growing area. If you remember, of the former president of USA, Jimmy Carter, was treated for using immunotherapy techniques. And in his case, he was cured as a result of. So this is a fast evolving area of immunotherapy. The cancer cells are coated with sugar, sialic acid, and that prevents detection by your antibodies of cancer cells. And now there are new techniques being developed to shave off these sialic acid molecules so that the detection becomes easier. So all sorts of exciting things are happening today. So for instance, if आपने वो जुगनू को रात को चमकते हुए देखा होगा, luciferin is the molecule which is responsible. It reacts with oxygen. Oxyluciferin बनता है, and there's an enzyme called luciferase involved. So the same chemistry is taking place in deep sea jellyfishes, which sparkle at the bottom of the oceans. And some scientists have taken the genes from these deep sea jellyfishes and inserted them into flowers, orchids, and lo and behold, you have luminescent orchids which glow in the dark like fireflies. This is a fast evolving area now. For instance, if you walk around the beaches of Karachi, you find seaweeds and some other plants growing happily in saline soils. Because nature has endowed them with mechanisms for salt tolerance. There are special efflux pumps and other mechanisms for salt tolerance. Can we identify those genes? Can we insert them into edible crops like fruits and vegetables? Because there's no shortage of water on our planet. There's plenty of water, but it's seawater. And if you can grow edible materials using seawater, then there could be a huge leap forward. So that's again an area in which we are involved in the university. If you also come to our institute, you'll find tens of thousands of orchids growing there. Orchids produced not by seeds, but by plant tissue culture. And this is again a technique for mass multiplication of plants. And you must have heard about GM crops and BT cotton, where you have natural pesticides built into cotton so that you don't have to spray them with pesticides. So this field of biotechnology allows you to tailor new plants and animals. Golden rice with provitamin A built into this is saving lives of many children who used to die because of vitamin A deficiency. And why do you get crops such as certain fruits and vegetables, for instance mangoes, सिर्फ गर्मी में मिलते हैं, सर्दी में नहीं मिलते? क्या वजह है? अल्लाह ताला ने, कुदरत ने उनके अंदर एक बायोलॉजिकल क्लॉक ऐसा डाल रखा है जो उनको हुक्म देता है chemical signals. So actually all that I'm talking about is organic chemistry. It is my field, although I'm just talking about it from a different perspective. So ek hukum deta hai, chemical signaling, which tells the plants when to flower, when to fruit. So this is genetically controlled. So DET1 gene is one that is responsible, but there are other genes also. And now that scientists are learning how to turn these genes on and off, the day is not far when you'll get fruits around the year. You'll be able to engineer plants in that manner. Gene therapy is being used also to detect breast cancer. The modified spider proteins have been combined with these very firefly proteins that I talked about, and they make cancer cells luminous. And that's, so those cancer cells which may not be removed by surgeons because they are too small in number and not easily detectable can be made visible in this manner. And malaria is also being tackled using genetically modified mosquitoes. Similarly, cows, genetically modified cows that produce milk which is very similar to human milk. The causes of obesity have also been linked to genes, the obesity genes, and also to viruses. Adenovirus 36, for instance, is one which has been responsible for certain types of obesity in children. And brown fat, which is the good fat, and burns all your calories much faster, was found to decrease in quantity as you grow old, and scientists are now learning how to change normal fat into brown fat so that you can remain relatively lean and slim and yet be able to eat much more. Aging now, of course, is also again being understood. There are many causes of aging. जो उम्र रसीदी का अमल है बहुत सारी वजूहात से होता है जिसके अंदर oxygen is one of the molecules responsible, oxygen radicals which attack your DNA, leading to deterioration, formation of oxythymidines and oxyuridines, etc. So hence the antioxidants come in. Vitamin C, for instance, is one. Apoptosis, as a doctor, you would have all read about this, as well as telomere, which erodes as you grow old, and there are methods now available to activate the enzyme telomerase to put this telomere back on, which is a protective cap on your DNA. And there are many genes, aging genes have been identified. And trying to understand the chemistry of aging has led to a number of exciting molecules as well. Resveratrol, which you find in red grapes, nicotinamide adenine dinucleotide, metformin, an anti-diabetic drug, which is very familiar, was also found to extend the life of animals, and rapamycin, which is also has found to have anti-aging effects, especially age-related diseases. So some of these molecules are undergoing clinical trials, and for instance, resveratrol, when given to mice, aging mice, was found to change their body features, and so that they started looking very young, behaving young, and so you can actually reverse the process of aging as well through some of these molecules. And it is thought that the children being born today may have ages of 120 to 150 years plus, so which may not be a good thing socially, but that's one of the areas that is evolving quite fast. Poliovirus has been re-engineered to treat cancer, glioblastoma, and synthetic biology has come in a big way, raising the possibilities, raising the questions, was the COVID virus synthetic that we experienced? It is certainly within the realm of synthetic biology to create COVID virus-like molecules, although the scientific evidence that it was artificially prepared is very weak. It probably was natural, from natural causes. Stem cells have come in a big way, including induced pluripotent stem cells. You can convert your skin cells or heart cells back to stem cells, and then redifferentiate them into the other types of cells through certain factors. And there is quite a nice stem cell lab in my laboratory where we have in the Panjwani Center for Molecular Medicine, which some of you might want to visit. And there is some very interesting work is going on. Is synthetic life around the corner? Craig Venter, for instance, in the USA, took the essential features of a bacterial genome, linked them together, and created an organism which could make 1 billion copies of itself. And you've heard of 3D printing, but now human organs can be produced by 3D printing. It's like an inkjet sprayer. You just take the person's own kidney cells or whatever cells and multiply them in this tank, and then you spray them layer by layer to create a living kidney. So this is part of a human kidney produced by 3D printing. तो जो मैजिक ऑफ साइंस की बात कर रहे थे डॉक्टर शाहिद, वो बिल्कुल सही थी कि अजीब व गरीब चीज़ें इस वक्त हो रही हैं. Amazing things are going on. Can you identify criminal tendencies by genetic analysis? The answer is yes, to a great extent you can, because 2 genes have been identified, of which one is the monoamine oxidase gene, and there's another one. And these are present in many of the criminals with violent behavior. So next time, जो job seekers होंगे, वो time आ रहा है कि अपना blood test से पता चल जाएगा कि does this person have violent tendencies or not. Here is an area which is very close to my heart, the human brain. About 100 billion neurons, each talking to some 10,000 other neurons. तो जितने सितारे हैं इस गैलेक्सी में, हमारी गैलेक्सी में, कोई 100 अरब, उतने ही तकरीबन न्यूरॉन्स हैं आपके अपने दिमाग के अंदर. और हर न्यूरॉन जो है वो 10,000 दूसरे न्यूरॉन्स के साथ गुफ्तगू कर रहा है. So 100 billion neurons communicating. So you have this arguably the most complex object of our universe is our own brain. So understanding the chemistry of what happens when you think, when you store knowledge, when you recall that knowledge, is a fascinating area of science, of neuroscience. And this is something that we have been involved in for the last 20 years, understanding the chemistry of thought. Thoughts are not abstract. Thoughts are made of atoms and molecules. What atoms? What molecules? We know a lot about where thoughts are stored, but we know very little about how, the chemistry of thought storage. And so we have been working on this for some years now. So this here is a person who's been given a task to solve a mathematical problem, and he's thinking. And so using functional MRI, some parts of his brain are lighting up. So this tells you which regions are involved. What you're actually seeing by MRI is the oxygen level, changes in blood oxygen levels. And if you look at a schizophrenic patient, you have a different pattern. And so you can see where the problems are in the brain in schizophrenic patients. And so what is the molecular basis of thought? So this is something about 20 years ago, I proposed that in the hypothalamus of the brain, there is a natural velvet. मखमल जो होती है ना, कपड़ा मखमल. तो कुदरत ने एक मखमल बना रखी है. What मखमल किस चीज़ की बनी हुई है? ये ग्लाइकोप्रोटीन्स होती हैं, protein backbone with various sugars attached, glucose, arabinose, fructose, xylose वगैरह. और इन sugars में बहुत सारे hydroxyl groups लगे होते हैं. So it's the velvet, the strands are the hydroxyl groups. तो आप समझे एक बहुत बड़ा, आप उसके दरमियान खड़े हैं, एक बहुत बड़ा जंगल है, और ये हाइड्रोक्सिल ग्रुप्स आपके चारों तरफ दरख्तों की तरह खड़े हुए हैं, और ये हवा से हिल रहे हैं. So they are in molecular motion. Now what happens is that when you look at an object, what we proposed was that through a process which is known as hydrogen bonding, patterns are formed, and these patterns are then frozen through hydrogen bonding. And hydrogen bonding is very common in nature. DNA would not be a double helix if it was not for hydrogen bonding between the two strands. Water would not be water If it was not for hydrogen bonding, it would exist as vapor, and so on. So it's a very common phenomena. And so what we proposed was that the glycoproteins are subjected to hydrogen bonding when you look at any image. And this results in the freezing of those images. जैसे कि मखमल पे आपने फूल के patterns बना देते हैं by pressing hot material on it, तो इस तरह ये एक patterns बन जाते हैं. And so when you look, when you learn, you have these, the conformational mobility of these sugars is frozen, creating these patterns. And logic then becomes a relationship of these patterns with one another. So this is a fascinating area. Sorry. I think I'm going the wrong way. Yeah. And this led us to propose this hypothesis, and there is growing evidence that this may indeed be the basis of thought storage and thought recall, and that partly folded proteins are involved. ये जो proteins हैं ये fold होती हैं, and there are certain other proteins called chaperone proteins which assist in the folding process. And so these were published about 2 decades ago. This mechanisms of thought storage that we had proposed at that time, and the fact that logic would then be a multi-dimensional overlay of these patterns formed through folded proteins. And there are many reviews that have come out as a result. Those who are interested, I would be happy to share them with you, that reviews that I have contributed and also papers. We have about more than 20 US patents on neurodegenerative diseases, because this then took us into areas like epilepsy, and more recently into Alzheimer's and Parkinson's, trying to understand what exactly is going on there. And so this was a paper published just very recently, in which they showed that indeed it is certain proteins which are involved in the storage of long-term memory and in synaptic plasticity. So we have in our institute, we started to look at epilepsy. There is a plant, the tubers of which are worn like a necklace, and using, which indicated by patients who suffer from epilepsy, and it seems to be of benefit. So working on the extracts of this plant, we isolated using this technique. We have in our institute a patch clamp facility, which means that you can excite individual neurons with very weak currents of 10 to the minus 12th of an ampere. जब ये आप इन neurons को excite करते हैं, तो they go uncontrolled repetitive firing, just like in epilepsy. Epilepsy में होता क्या है? It undergoes this uncontrolled repetitive firing. And so you can then induce epileptic-like seizures behavior in these neurons, and you can do this in the presence or in the absence of potential drugs, plant extracts or purified compound, and see if it can suppress this activity. And so using this technique, we then isolated the active compound, we synthesized libraries, and then they went through clinical trials. They are into phase 2 clinical trials now, but they are very effective. And now we have developed some gadgets through which you can actually just spray them, a nasal spray based on these compounds, which has an instantaneous and very positive effect in controlling epilepsy. This is just one of the patents. So going on to what is happening, people can drive now cars using just thought control. They wear a device, a special kind of hat, and you have this gentleman with a device around his head, and he's just giving commands, mental commands to the car: go, fast, slow, turn right, left, and he's driving this car through reading of the encephalographic signals of the brain and the blood pressure changes by these devices. Artificial intelligence has come in a big way. According to a McKinsey global report, there'll be an impact of some $15.6 trillion of AI alone internationally in various fields. And So if Pakistan can capture even 1% of this huge market, there's $160 billion worth of market, just if you can capture 1% of the AI international market. So, and this is finding many applications in cancer detection, for instance, looking for breast cancer using AI tools. It has also been used. IBM has actually created a software which has been used both in medicine and in law. And this has been there for the last 5 years or more. And this is being used to diagnose different diseases with great accuracy. Similarly, legal cases through a different software can be solved information can be provided very quickly through IBM Watson's law services. So the time is coming when you will have, as very powerful tools as doctors, access to AI to look at past literature and also to look at the symptoms of your patient and be able to, using AI, tell which is the best treatment for this person. The blind are able to see with the tongue. That again is an amazing thing. Actually, you see with your brain, you don't see with your eyes. It's only a mechanism for image transfer. The eyes are only a mechanism for image transfer. And so there are these devices which have been developed about a decade ago. They're commercially available. This lady is wearing glasses with a little camera which takes in the optical signals which are converted into electrical signals. And then she has in her hands a lollipop-like device which has some 400 sensors. The moment that she puts it on her tongue, the image is transferred through the nervous system of the tongue to the brain, restoring partial eyesight. This lady, these are real-time translation devices which one can put in one's ear, and there are many companies making them. So this lady is talking to a Chinese. She talks in Chinese. Sorry, she talks in English. And he has a similar device, this instantaneous translation, and he hears in English and vice versa. So instantaneously, and these are available in many languages. So you can just wear a little device if you go abroad, and then you can communicate effectively with persons who don't understand English. Wrinkle zapping creams have been developed. You're aging and you have wrinkles on your face. You just put this cream on and the wrinkles disappear instantaneously. Come back in the evening, wash your face and the wrinkles reappear. Ultra-long drug delivery molecule. I've deliberately chosen most examples from medicine which may be of interest to you. I could talk about materials and other areas as well. Ultra-long delivery materials. So these are special polymeric gels. So capsules dissolve slowly over a period of 2, 3, or 4 weeks. So now these slow release drug molecules. So instead of taking tablets every day, you may in the future be taking a tablet which is coated with these, which will release this slowly and release it over 2-3 weeks. Paracetamol तो अभी भी मिलती है इस तरह जो आपको थोड़ा सा 8 घंटे तक करता है, लेकिन ऐसे और भी there are now these kind of drugs with these kind of polymeric gels which are being developed for dialysis. Wearable kidney machines are being developed, which you can wear under a coat. So it's constant dialysis taking place all the time. You don't have to go and get dialyzed. Cut off the tail of a lizard, it grows back. Cut off the hand of a person, it does not grow back. क्या वजह है? Scientists have discovered there are some microRNA switches which are activated in the case of a lizard. And these result in regrowth of the organ. And now scientists are looking for similar microRNA switches in humans. Do they exist? Question mark. Let me now talk to you a little bit about some of the other areas. I have 10 minutes more. I was given 40 minutes to have another 10 minutes more. So we live in an age now where knowledge has become far more important than natural resources. And countries which have realized that their real wealth lies in their children and are investing in education, in science, in technology, and in innovation and entrepreneurship are the ones that are moving forward. Pakistan has a population of about 220 million. About 60% plus of our population is below the age of 30. So we have a very large young population. So this is a demographic advantage that we have, which this window is open for another 20 years or so before this whole, this becomes a burden rather than an advantage. And so that this is the time that we must unleash the creative skills of our children through proper education. And so whether it's large countries like China or small countries like Singapore, the story is the same. Knowledge driving economies. And so this is the report I mentioned, the McKinsey Global Report, which talked about $100 trillion impact of some of these new technologies, including next generation genomics, advanced agriculture, materials engineering, energy, artificial intelligence, etc. And $15.6 trillion impact of AI alone, which is already taking place. There was mention about Pakistan, so I thought I'll just show you a few slides of when I was appointed as the Minister for Science from 2000 to 2002, and later when I was the first founding chairman of Higher Education Commission. I convinced President Musharraf to buy 1 or 2 less F-16s and invest the money in education. I would have liked it to have been invested in school level education also, because that's where the pyramid starts. But I was just responsible for higher education. But in any case, there was a 6,000% increase in the development budget of science and technology during that time, and later a 3,500% increase in the development budget of higher education, which allowed us to send some 11,000 of our brightest men and women abroad to leading universities. We had the world's largest Fulbright program, a $150 million program. Half of it was being provided by HEC. And these students who went and did their doctorates or were sent for postdoctoral came back, and then a major change started happening in the universities of Pakistan. And that's another lecture, so I don't want to spend time on that. But this, I think, slide is very interesting. On the extreme left is the year 2000. Extreme right is 2020. And the green is Pakistan, the red is India. And this is international publications in impact factor journals per capita, per 10 million individuals. And as you see, we were about, in the year 2000, we had only 44 international publications per 10 million population versus 172 of India. So we were about 400% behind India. But then things started changing, and we are now comparable to India. We, according to the Web of Science data, we overtook India in 2017 or 18. In real numbers, we are still 5 or 6-fold behind. So this is only per capita. In real numbers, India has about 6-fold publications higher. But in per capita, we have caught up. And the other database, Scopus, the graph is the same. So both Web of Science and Scopus data shows that we are now about at par with India, which is no small achievement for Pakistan. And this happened because of our primary focus was faculty. Universities जो हैं खूबसूरत इमारतों का नाम नहीं होती, खूबसूरत दिमागों का नाम होती हैं. It is the quality of the faculty and the creativity of the faculty that really determines the quality of a university. And so that's where we focused on. We sent a large number of students abroad, attracted them back by excellent salaries. At that time, they were 4 to 5 times the salaries of a federal minister in the government. Excellent research funding. Every student who was coming back could apply for a $100,000 research grant. So that even if he or she came back to a weak university, they would have sizable research funds to get the ball rolling. Digital libraries were set up to provide free access to 65,000 textbooks and 25,000 international journals with back volumes, and free access to sophisticated instrumentation and other measures. And these all contributed to that graph that I talked about. The PERN was set up, Pakistan Educational Research Network, We placed Pakistan's first satellite in space, PakSat-1. Part of it was used for education and had a link up with all the universities. And I was just mentioning to Dr. Shahid Parvez Saab that we have a lecture system going on where every day several lectures are delivered by eminent experts from both Pakistan and abroad. And these are listened to live and interactively in our universities. So that focal point for distance education is my institute. And I was suggesting to Dr. Shahid, Professor Shahid, that some of you might want to deliver these lectures or persuade your friends abroad. And these are then, there's a focal point in every university, and they are informed a month in advance who is going to talk on which subject and at what time. And these are also recorded and put on the web, so you can then, the students can then go through them again. So this is a national hub for distance education. And we have also set up an integrated version of MOOCs, Massive Open Online Courses, which is being widely used by our students across Pakistan and across the world. And right now there are some 3,000 Khan Academy courses which are being translated into Urdu as well. So these developments were applauded by the UN Commission on Science, Technology and Development, by Thomson Reuters, and there are many other positive reports about what was happening in Pakistan. India became concerned at what was going on at that time, and there was a cabinet meeting, and this was published in the Hindustan Times about that there's a threat from Pakistan to Indian science. I don't think that there is any threat at all. I think India has been far ahead in science than Pakistan, but we did make some good progress. Also, I think we and India should start working together to try to set politics aside and work as brothers and sisters in arms to solve problems which both our countries face. Just last 2-3 minutes, I'm setting up a number of new universities right now, so I'm involved deeply in that. These are very interesting universities. This is the Pakistan-Austrian Fachhochschule, which has 3 streams. This is set up in Haripur. It has collaboration with 8 universities. 8 ghair-mulki universities se collaboration hai. What we have done is asked each one of those foreign universities to godfather the development of one department. So, एक foreign university जो है Austria की से वो जो है that will be developing the department of the computer science and AI department. Will be training the faculty, will be involved in quality assurance, and eventually will be giving its degrees. So student in one department will get degree from one foreign university, student in another department will get a degree from another foreign university without, so this is a very strange and the first university of its kind. So it has a high technology, which is a Fachhochschule, which is bachelor's and master's. It has full-fledged engineering, which is PhD and postdoctoral in engineering. And the heart of the university is a technology park with some $10 million set aside for new product development. So these are the various collaborating universities, and we have cherry-picked the strongest departments in the best universities in these countries to collaborate with us. And now a similar university I'm in the process of establishing in Sialkot, and we are discussing about possibility of one in Karachi also. This I think is my last slide. Well, our institute, we have had 2 fellows of the Royal Society, we have had 1 UNESCO Science Prize, and we have had 27 civil awards, just one institute in Karachi, including 1 Nishan-e-Imtiyaz, 4 Hilal-e-Imtiyaz, 13 Sitara-e-Imtiyaz, 1 Pride of Performance, 8 Tamga-e-Imtiyaz, and 10 DSCs from foreign universities, including Cambridge University and others. So it's I hope that some of you should come over and visit this facility. There are some 600 students doing PhD there, and there are about 20 different buildings. There's a center for virology, there's a center for genomics, Center for Molecular Medicine, Panjwani Center. HEJ, of course, is the original chemistry institute, a nanotechnology center which has been established, and a whole range of other centers. So it's very interesting, and I think, for instance, those of you in molecular pathology particularly, we have about 20 different mass spectrometers. We have 13 superconducting nuclear magnetic resonance spectrometers, and so on. So this could be quite interesting to many of you who want to go deep into the understanding of some of the pathological disorders, especially at the molecular level, because we have very good analytical facilities. And we have had a large number of scientists. We have had about 120 German scientists who have come to work in our institute in the last 5 or 6 years. The gentleman in the center is Professor Tsuda. He stayed with us for 5 years from Japan. And so all the time, there are many, many foreign scientists working here. So my time is up. Just in the last half a minute, I'd like to say that it's an exciting world of science that we live in. I've just given you a flash of this wondrous world of science, which, as Professor Shahid said, is magical in many ways. Trying to understand it and exploring new horizons is something that I have enjoyed doing all my life, and I hope you too would do that. So thank you very much. Assalamu alaikum.
Thank you, Professor Ataur Rahman. Can you please stay on the stage? I request Dr. Shahid Parvez to please come and present a small token of appreciation to Professor Ataur Rahman. Thank you once again, Professor Ataur Rahman and Professor Shahid Parvez.
I would now start the keynote sessions. Each keynote session is of 30 minutes. First of all, I would request Dr. Naila Kiani, President, Histopathology and Cytopathology Society of Pakistan, to come on the stage and introduce the first speaker. Thank you.
Assalamu alaikum. It is my pleasure to introduce Professor Anil Parwani. He is affiliated currently with the Ohio State University. He's a director of anatomic pathology and also director of pathology informatics and digital pathology at the James Cancer Hospital. He had his formal training at Johns Hopkins University. His research is focused on diagnostics in kidney, bladder, and prostate cancer. Dr. Parwani has expertise in the area of anatomic pathology, informatics, including designing quality assurance tools, biobanking informatics, clinical and research data integration, applications of whole slide imaging, and digital imaging, telepathology, image analysis, and lab automation. The title of his presentation today is Emerging Role of Digital Pathology and Artificial Intelligence in Pathology Diagnostics, Education, and Research. I would now request Professor Anil Parwani to come onto the stage.
Good evening. It's a pleasure to be here. It's an honor to be here. This is my first meeting with PAP, but I'm very, very impressed by the quality of the program and the way this conference has been put together. So I will be talking to you today about artificial intelligence and digital pathology, and I couldn't agree more with Dr. Ataur Rahman about the power of science and the power of technology. When I was in school in Karachi, I was always interested in science, but what I see out there in the world is very, very exciting. So I want to give you a glimpse of where I'm coming from, Columbus, Ohio. I am from Pakistan, but now I live in Columbus, Ohio, at the Ohio State University, which is one of the largest universities in the world, 70,000 students. So what you see in the field is a football game, which is going on, and the city itself. So I want to give you an overview of the evolution of digital pathology. And AI and how are we using it today as pathologists? What are the challenges? What are the opportunities? How can we harness the power of AI to help us as physicians and as lab professionals and explore the future, which is very, very exciting. So pathology is transforming. As you saw from our previous lecture, there are so many exciting things which are being built in the lab, in medicine and health science, but pathology in particular is gone a rapid transformation in the last 5 years. So there are exciting tools and innovations. If you look at your test menu, there are more complexities in the testing. There is more automation. I'm going to focus today mostly on computational pathology and artificial intelligence. So in terms of tumor itself, when you classify these tumors, now we can sequence these tumors within a day, within hours. So there is more knowledge, more discoveries, and as a pathologist, you are contributing more and more towards the therapeutics of the patient. We can decipher, if you're looking at two tumors, they look exactly the same. But with the knowledge that we have today, we can provide more meaningful information to the oncologist who treats these patients. As a pathologist, we are very visual, right? So when I learned my pathology, when I went through residency program, when I went through medical school, pathology is very visual. We look at H&E slides, we look at cramp stains, we look at all kinds of special stains, and we create a pattern recognition. And AI is really training the computer to learn these patterns that we've learned. But as a pathologist, I love my microscope. I don't want to give it up. And many of you have microscopes, you have cameras on your microscope, so you are practicing digital pathology. So for a pathologist, anatomical pathologist, when they look at a slide under a microscope, that's like a good history and physical that a family physician takes. So we're not taking away the microscope, we're just introducing a way for us to process that information visually. Just like in the previous lecture, we heard about your tongue, it can be used as an eye. It's just an image processing device, right? So as I report out, our reports are becoming more complex. The knowledge that we have today as pathologists is much more complicated. So how can AI help us? And we have more pressure today to give the diagnosis, and it has to be fast, it has to be good, it has to be better. How do we get to the point where we can harness the power of these technologies to help us get to a better diagnosis, get us to a better quality diagnosis, not just a fast diagnosis? So what are the challenges in pathology today, right? Especially anatomical pathology. We don't have standardization. The barcodes on your slides, if there are any, are very different. If you get a patient from one hospital to another, their medical records are not easily transferable. Diagnosis is still very subjective. It's based on quantitatively analyzing each slide. We have a shortage of pathologists worldwide. Pathologists claim they are overworked. How many pathologists in the room who think they are not overworked? Who think they have a good life, they don't need more work? And we have an explosion of medical knowledge. Time-consuming tasks like counting cells. How can AI help us? Standardization, more objective diagnosis, more automation, more accuracy. That's the goal, right? Are we able to achieve it? So today I'm going to show you examples from my practice, and how do we keep up with this knowledge, right? And are we ready to give up your microscope? Who's ready to give up your microscope? You are, okay. We have at least one or two pathologists who are ready to give up their microscope. All right, so let's look at, I'm going to talk to you about AI-powered pathology. And this is not science fiction, this is a reality, this is happening. It's happening in a very big way. So when I talk about digital pathology, we're talking about a dynamic image-based environment, which enables the acquisition, management, and interpretation of pathology information, which is generated from a digitized glass slide. People have used the term virtual microscopy or whole slide images. There are different types of technologies where a robot can control the slide. A robotic stage could be controlled remotely by a pathologist. So when even in Karachi, I can see cases in Columbus, Ohio. If a neurosurgeon is performing surgery and they need my expert opinion, I can go and control that microscope from here and help the patient right there. And whole slide imaging is a particular technology I want to focus on today, which is a single high magnification digital image of the entire slide. So there are different types of devices out there. Many of you have a camera on your microscopes. You're practicing digital pathology. Many of us now are able to use whole slide imaging, but we also have smaller devices which can allow you to take one slide and have it digitally available to share it with a colleague. And then you can start analyzing this. You can start applying artificial intelligence. So these are some examples of whole slide scanners. So when I was in medical school or residency, only one or two companies were making these scanners. But this is now around the world, there are companies who are making these devices. Probably some of them are in the exhibit hall. But look at the resolution of these images. So I'm a GU pathologist. When I look at a cell, I'm looking inside the nucleus. I want to look at nucleoli. So with these newer scanners, you can achieve a spatial sampling period of between 0.25 to 0.5 microns per pixel, which is amazing because that's very, very good resolution. You know, when I was a resident, we didn't have this type of a resolution for these images. We can also do 3D imaging now. This is Z-stacking. So you're scanning slides at multiple planes. So for cytology, for neuropathology, for hematology, this is very, very important. So there are new scanners which can achieve Z-stacking, and they can achieve it at this resolution. So you're not giving up your microscope. So most of the pathologists who said they don't want to give up the microscope, they're not really giving it up because your microscope is inside this box. So you're not really giving it up. So once you take your glass slide, you can start creating a pixel pipeline, which allows you to do computational pathology, where you can combine data from genomics, from images, and bring it together for diagnosis. And you can do it with the possibility of sharing it from anywhere in the world. So this morning, when we were doing our workshop, I was able to send a link to pathologists, residents, trainees, much before the time, and they were able to look at these images while we were in the lecture, on their own smartphones and on their tablets. So just a few terminologies. When we talk about AI, we're talking about machine intelligence in contrast to natural intelligence. We're also talking about what are the goals of AI research, right? Professor Rahman was talking about a lot of these possibilities, particularly in medicine. But when we talk about deep learning, we're talking about deep structured learning or hierarchical learning. And this can be supervised, semi-supervised, or unsupervised. Unsupervised is really powerful because you're not training the computer to look for a specific feature. If you're looking for prostate cancer detection, you're not training the system to recognize one feature, but allowing the AI systems to learn from itself. So in pathology particularly, whenever we have new technologies, we are threatened by it. We think this technology will take it over, right? So for example, immunohistochemistry. When they were first introduced, pathologists were afraid that everybody will just order a bunch of immunostains and we will lose our jobs. When genomics started, we started sequencing these genes and cancers, pathologists were concerned at that time, but that was the second revolution in pathology. So AI is the third revolution in pathology, and we're just in the very infancy of this revolution. Interestingly, if you look at the microscope many years ago, people thought microscopes were a disruptive technology. So we go through these hype cycles, we go through these cycles of innovations, and pathology is no different than any other field. So in terms of what can this help us to do? When you look at a slide under the microscope, you need the information about this patient. When the slide is digitized, not only can you share the image data, but you can share everything else about this patient. So in my lab, most of the pathologists are now not using a microscope. All the slides are digitally available to them. But we don't need to do a full-scale digital adoption to harness the power of AI. So once the slides are digitized, pathologists have access to AI tools which they cannot do with the glass slides. We can start to think about AI assisting the pathologist. We can think about AI augmenting your diagnosis or autonomous diagnoses, which is already happening in pathology in some areas like cytology, where the machine screens the PAP smears for you. What about education, right? So once these tools are integrated, they will become routinely available. What about trainees who are learning from it? Huge impact on education, right? So we talked about digital library of lectures, but imagine if every pathologist in the world was able to digitally make their slides available, we would have a huge archive. So in my university alone, we have 3 million images available to residents for education and training. In order for this to occur, you also need information to be integrated with the images, with the lab information system, and all the tools that you might need. So on your smartphone today, you have many apps. So think about this as apps which could be used for you. If you're a soft tissue pathologist, you want to count mitosis. So today there are apps which will enable you to do this. It's not working there. Can we move to the next slide? It's not, it's not moving from here. Okay, now it's good. So when you present this information in the context of the patient's data, the clinical information, the PSA level, these images will become more meaningful. But if you are just scanning slides, they are of limited value. Okay, so once the slides are digitized, there are impacts on education, there are impacts on the clinical workflow. You can get a second opinion from anyone in the world. You can have access to AI tools. You can have access to tumor boards, just like radiology. When radiology became filmless, they gave up their films. In pathology, we are not ready to give up our glass slides yet. But once the slides are digitized, we don't need to move the slides around. And you can start thinking about AI. So this is a resident in my hospital who is now learning from digital slides. So we have over 200 primary diagnosis sign-outs in a typical day. Nearly 80 consults signed out. This technology supports numerous tumor boards, and these images are available for multiple research projects. You know, we used to have glass slides, and we used to do research. We used to share the glass slides, and it was always, these slides would often get lost or they would get broken. But with digital slides, they're available to multiple users at the same time. The consults can be done by multiple pathologists looking at the same image and interacting with each other. So this is a great educational opportunity with an integrated workflow. So once the slides are digitized, what else can you do with this, right? So when you've created the pixel pipeline, let's say every pathologist has now bought a scanner and your slides are all digital. Let's talk about that future, that possibilities. you can now actually start to think about AI tools to help you. So going beyond the glass slide, we can now get algorithms, which many of them are now commercially available. In the United States, 3 scanners are now approved for primary diagnosis. There are several commercially available algorithms. There are also algorithms that have been built in universities by machine learning scientists, by artificial intelligence institutes. At my institute, we have an AI program. We are starting a master's program in computational pathology. But we can think about all these algorithms which can now be used to help build and identify tools. So are we ready for that disruption in pathology? Are we ready for augmented pathology which is powered by AI? So in my opinion, we're already there in many ways. What can it do for pathologists? We have more time to do things that matter, and pathologists can now have more time to spend on their cases. We can start to work as a physician with oncologists and radiologists, and more importantly, produce objective and more reproducible results. So how can AI help pathologists today? We do a lot of counting, right? Who loves counting cells? Nobody. So we can automate a lot of the complex tasks that we do routinely, and we can make them more objective than ever before. So look at this screen here, right? So this is a patient with breast cancer, and you're looking at multiple cells, and some of them are positive, some of them are negative. So if I ask each one of you in the audience to give me a percentage of positive cells, or 1 plus, or 2 plus, and 3 plus, I'm going to get 300 different answers. With this, I'm just going to be able to press a button and get the exact answer every time. It doesn't matter where you are, whether you're in Cleveland Clinic, or Aga Khan, or at Ohio State. Everybody will get a very similar answer. Maybe not exactly to the percentage, but it's going to be so much more standardized and more objective. Because we're going to give drugs to these patients which are thousands of dollars worth. And they're not easy drugs to give. So I think the time has come to start making pathology more objective. So this is image analysis, where you can quantitate results, nuclear and membrane. And you can do this very rapidly. And this is a technology which is based on machine learning, which is based on image analysis. And it was a technology which was built 20, 25 years ago, or even more. In the current state, we can quantitate things very easily. But in the future state, we can think about focusing on very specific regions, which are what we call hotspots, and do this for the entire slide. Right now, we do it for a region, and we get highlighted regions. We can score them. So once you do this, you can produce standardized diagnostic tests, which are transferable across the world. What about treatment of patients, right? So surgeons will ask you, oncologists will ask you, how much necrosis is there? Is there a treatment effect? How much is the treatment effect? And we give them an estimate that oncologists might get a second opinion, and they might get a different answer. With this technology, you can give the precise diagnosis. You have 25.7% necrosis in this patient. When the patient gets more treatment, now it's 72.3%. So we can move towards more objectivity. And so I'm not saying traditional pathology is inaccurate. What I'm saying is this technology helps us do this faster and better. What about reporting, right? So we report your results as pathologists. We can now start integrating this in the pathology reports within the lab information system in real time. So this is an example of a software that we are testing at our hospital, where before I even come to my office, the computer has screened the prostate biopsies and has alerted me that 2 of these are suspicious. 1 of them is cancer, 3 of them are benign, and has also helped me quantitate the cancer, if there is any cancer. But it's not replacing me as a pathologist. It's helping me it's augmenting my, or assisting me in my diagnosis. So what about reporting in pathology, right? So we take pictures in the gross room, right? This is a patient with colon cancer. So imagine a world where your polyps, when you take them from the colon, you can point to those and you can link them into your report. So when you click on the report, you can actually see where the slide was taken from and what polyp was malignant, what polyp was not malignant, right? So you can go back to radiology and endoscopy and create a complete chain of events for these different tumors. So it's really, really, really powerful technology. What about image retrieval, right? So we search many, many times. On an average day, you probably use Google multiple times every day, right? You're looking for the best pizza in Karachi, you're looking for directions, you're looking for an app to choose the tie that you're going to wear today to work. So there are many, many applications. But imagine a tool where a slide is scanned and you can now put that image into Google and Google will find the most similar images for you. So when I was a resident, I used to look at the slide under the microscope. I used to open up books and try to find which tumor does this look like. You know, this looks like a leiomyosarcoma. But you don't have to do that anymore because technologies like this help us with intelligent searches, just like you do today. So this will be the future where you are looking at a case and on your monitor, you circle an area and you click that circle and the computer will find similar tumors for you and create a database for you. How are we doing on time? I wasn't keeping track. We have 5 minutes. Okay. All right, so let's look at beyond this, right? So what else can we do? So what can we do which is possible today and what will be possible tomorrow? So what I have shown you today is something we can do today. These technologies are becoming more mainstream. I understand not all labs have scanners. So I'm not here to tell you that every lab should go out and buy a scanner. But what I'm trying to tell you is giving you a glimpse of what the possibilities are. When your workload is digitized, you can share the images, you can analyze the images, and more importantly, you can start using artificial intelligence. But imagine a world beyond whole slide images, where you don't even have to stain, where you don't even have to make glass slides. So this is an example of a technology which is using a knife. So I'm going to show you this technology. So, okay, so this video is not working. All right, so let's go, okay. So what you're looking at is a piece of tissue which has been stained, which has been paraffinized in a block, and you're staining this tissue underwater. And you're making slices of it. Let's go to the next slide. So these are examples of tissues where you haven't made any glass slide. The tissue has been directly stained with H&E. And you can use different types of stains. And this is how it's working. So the tissue is being cut underwater with a diamond knife. And this technology is called knife edge scanning. As the tissue is being cut into a slice, it's being scanned underwater by the camera. And what you see is an H&E image where no glass slides are made. So you've gone directly from gross pathology to the tissue to an image. And now this image can be shared by anyone. So we're not there to use this in clinical settings yet. This is more of a research which is being done at university. But these types of technologies are making their way into pathology. And as pathologists, we have to really own this space. We have to understand these technologies. If we don't understand and use these technologies, somebody else will, right? Some other profession will use it. So these are examples of a study that we did where we compared diagnosis of the pathologist from 3 different institutes with an AI-based diagnostic algorithm. And they were very, very accurate in comparisons. So this is the current state, AI tools for prostate pathology. We have at least 3 commercially available tools now around the world. But going beyond that, the future state will be we can reach to a single cell level spatiomics, where we're not only scanning the slide, we're interrogating a single cell and generating data at a single cell level. What about multiplexing? What about other tools that are available in pathology? Mostly in the research setting, but they're making their way into the clinical side. So with multiplexing, you can interrogate a single cell for multiple targets and see which proteins are upregulated, which proteins are downregulated, and create molecular signals. Or we talk about genomics, but now we're in the world of imageomics. So if you combine image data and you combine it with other types of omics, you have a more powerful tool set available to make the diagnosis and for research. So pathology diagnosis will be redefined, and it will help pathologists in many ways. So when we talk about pathology and the power of using AI, it's not just being a more objective, but accurate, timely, and trusted. So when I make a diagnosis, the same diagnosis can be made by another pathologist, and we can compare it more easily. The standardization will be across the board. So putting it all together, this could be your office in the future, where information is coming from multiple sources. If you're a molecular pathologist, the screens might have different data. If you're a soft tissue pathologist, the screens might have different data. So these are some examples of tools that will help us provide assistance, augmenting our diagnosis, or autonomous diagnosis. But they're not replacing pathologists. So the number one reason pathologists are afraid of AI is, and I can ask you to raise your hands, but I know the answer, is many of us are afraid of the unknown. We're afraid of what's inside the box. Who is making that diagnosis? It's really you who should be making the diagnosis. But these are tools, just like your calculator, just like your GPS, just like your Google. These tools should be working for you every day. I know we don't have this technology worldwide yet, but this is why we really need to look at it, what we can do today, what we can do tomorrow, and what we can do in the future. Because change is not easy, right? Nobody likes change. Everybody likes their routine, they want to go to work, they want to make their diagnosis. Everybody loves their microscope. But the time is here to transform the pathology lab and create the lab of the future. And it's an exciting journey, and we should not be afraid of it. So with this, I'm going to stop. I know I went a little bit over. So I want to, again, thank you all for being a great audience. I want to thank the committee, the program committee. I want to thank the PAP for having this wonderful conference. And I'm hoping to learn a lot also as I attend all these lectures and I go to the exhibit hall. And I look forward to interacting with many of you. So thank you for the invitation, and thank you for inviting me here.
Thank you very much, Dr. Anil Parwani. In the past 2 years, we have lost 2 of our eminent pathologists, Professor Sheema Hassan and Professor Tahir Shamsi. Dr. Sheema Hassan was a towering personality in histopathology. Her encyclopedic knowledge of subject and brilliant diagnostic skills made her a histopathologist par excellence, and her passion elevated her work to a high pedestal which very few can attain. She benefited many from her knowledge, expertise, and vast experience. This first-hand learning under her enabled many of them to become high-caliber histopathologists, with many of them holding high academic services positions in various major national and international institutes. Dr. Sheema Hassan's legacy of excellence will endure. We have a small memento of appreciation to recognize her tremendous contributions. We have Dr. Shima Hassan's son, Mr. Heather here. I'd request him to please come on the stage and to receive this small momentum. I'd request Dr. Shahid Parvez to please come on the stage and present this momentum to him.
Only son of Professor Shima, PhD in mathematics, working at NED. So you are her legacy, and I must say that we all miss her very much. So may Allah bless her and Janatul Firdaus with our son.
Late Professor Tahir Shamsi was a leading clinical hematologist and transplant physician of Pakistan. He was one of the few who came back to his country to treat his own. He was a dedicated physician and academic leader. He founded National Institute of Blood Disease in 2008 with the vision to provide the best possible healthcare facilities to patients with blood diseases. He wanted it to be a center of excellence for teaching, training, and research in the field of hematology, for which he tirelessly worked throughout his career and achieved it quite remarkably. He will always be remembered as a great mentor, colleague, friend, and a physician by all of us. We also have his son here. I request him to please come on the stage. And I request Dr. Suhair Chugtai to please come on the stage and present this memento to him.
Left a legacy behind. There's so much that he contributed to the field of hematology, diagnostic as well as clinical. There's so much more that he wanted to do, but untimely death has left a huge vacuum. But I must congratulate Osama, although not a physician himself, but he's striving to carry his legacy, and I wish him all the best. Thank you.
I request you all to please recite a small Fatiha for the departed souls. Ameen.
Jazakallah. I would now request Dr. Dina Jafri, Chair Scientific Committee, to proceed to the podium and introduce our next speaker. Thank you.
Assalamu alaikum and a very good evening to all of you. I would like to quickly introduce you all to the next speaker. The next speaker for the keynote talk, Professor Khusro Adeli. Dr. Khusro Adeli is the president of International Federation of Clinical Chemistry, that is IFCC, known as IFCC also. He's currently the division head of Clinical Biochemistry, Department of Pediatric Laboratory Medicine at the Hospital for Sick Children. He has held several other leadership positions in the University of Toronto. Dr. Adeli is a senior scientist and academic clinical biochemist with over 30 years of experience in clinical chemistry service, education, and research. One of the breakthrough achievements in our field has been the caliper reference interval for pediatrics, developed under his leadership in Canada, which is now being widely used worldwide, globally. The Pakistan Society of Chemical Pathology is honored to host him as the keynote speaker tomorrow and as our honorable guest in ChemCon 22. As chair of the organizing committee 2021, now I invite Dr. Khusro on the podium. The title of his talk is IFCC 70 Years of Global Leadership with New Vision, Strategic Direction Post-Pandemic. Dr.
Well, thank you very much for this opportunity. First of all, I want to thank, on behalf of the IFCC organization, thank the conference organizers for their kind invitation, particularly Professor, all of you, Lina, as well as Aisha and Hafsa, and a number of colleagues here in Pakistan. Pakistan is one of the members of IFCC organization, and so my goal today is to introduce you to IFCC. And it happens that this year we are celebrating our 70th anniversary. And I noticed you're also celebrating 75 years of pathology here in Pakistan, which is great. I'm here to introduce, happy to introduce this organization. Now, IFCC, this is the globe, map of the globe. All of the blue countries are members of IFCC. So most of the world is actually members of IFCC, including Pakistan. We have a total of currently 96 countries, 96 full members, but we also have affiliate members. So a total of about 120 societies are members of IFCC. And 56 corporate members as well. So IFCC is unique that we also have corporate members. All of the diagnostic companies you are aware of actually are members of IFCC, and we have a strong working relationship together. So we have committees where corporate members are represented. So we have a strong link with corporate, and because this is, after all, to the benefit of the patient and benefit of what we do, is to collaborate between academia and industry. As a whole, we represent approximately 45 to 50,000 laboratory specialists and pathologists. There is actually a similar organization that I'm sure our pathologist colleagues are familiar with, WASPAM, and actually we have a direct collaboration with WASPAM. We recently invited the president of WASPAM to attend the IFCC meeting, and we have a memorandum of agreement between the two organizations. So there's strong relationship between laboratory medicine specialists and pathologists within and between these organizations. Now, we are actually, the federation actually has 6 regional federations. So the largest regional federation is the European Federation, 41 societies within the European Federation. We have the Asia Pacific Federation, we have the Arab Federation, mostly Middle East and North Africa. And then we have a Latin American Federation. Almost all of the Latin American countries are members. And then we have the North American Federation. US and Canada form the North American Federation. All of them being part of the IFCC organization. Now, these are some of it's not the full list, but some of the 56 corporate members of the IFCC organization. And as I mentioned, we have a strong working relationship with them. Now, IFCC just this year is celebrating the 70th year, as I mentioned, and we actually held a conference in Brussels in Belgium just 3 weeks ago, last week of October. And we actually had representation from Pakistan. Dr. Aisha Habib was there, and as well as 2 young scientists from the Chemical Pathology Society were there with IFCC scholarships. So we actually celebrated the IFCC history. IFCC actually began initially in Europe, was formed in 1952, and so it's 70 years now. And it actually changed names over the time, but eventually was named IFCC, including laboratory medicine, because the truth is that we have societies other than clinical chemistry, so we have societies in other areas. So now named International Society of Clinical Chemistry and Laboratory Medicine. And these are the showing you the presidents of the IFCC organization, starting with Professor Earl King in 1952. And so it's been a long tradition of basically bringing countries around the world together and working together to promote this field. Now, I have a video about, I don't know if there is time to show you the video. Let me see. Sorry, let me go back. Perhaps not necessary because of the time. I know you're tired and there are many presentations. But anyways, we're happy to celebrate really 70 years of contribution to the field of laboratory medicine and pathology. And it has actually, IFCC has turned out to be the leading organization in the community of laboratory medicine. Now, this is the current IFCC executive, which includes not only president, secretary, and treasurer from different countries, but we also have representation, regional federation representation. So we have representation from each of those regions that I mentioned. And this is currently the sort of a strategic plan of the organization, focusing on being more proactive and trying to impact, truly impact the eventually patient care and public health. And so we have begun a number of new programs in the recent past, before the pandemic, and particularly now more active post-pandemic. And I just want to mention briefly some of that. But of course, immediately IFCC, when I became president in 2019, I was elected, we faced the pandemic immediately. So one thing IFCC has done is try to face this pandemic, this challenge, by actually supporting labs around the world. And so I want to share with you some of the activities of IFCC in relation to COVID-19. One of the first things we did in March 2020, when, as you know, WHO announced the COVID-19 pandemic, we actually formed a task force. And this task force has representation from around the world, and they've been working hard, and I've been part of it, to try to develop these practice guidelines, COVID-19 practice guidelines. So we have been publishing and developing guidelines on biosafety in clinical labs, molecular testing, serological testing, rapid antigen testing, as well as biochemical and hematological markers to monitor patients who are hospitalized with COVID-19. We created an online resource. It's still available on the IFCC website. If you go to ifcc.org, you can see the resource. This resource provides information on many aspects of COVID-19, on prevalence and rates around the world, on diagnosis, on monitoring, on mechanisms of various complications, and so on. So it is quite up to date. I welcome you to take a look if interested. We also developed this. We actually so this is actually the names of the task force members and some of the guidelines that were published. They were all published in this journal called Clinical Chemistry and Laboratory Medicine, which is published in Europe, but it's an international journal. And these are, actually there are additional papers. There have been more than a dozen papers. Some of the main ones are listed here that I've already mentioned. We also had actually held a conference, a COVID-19 conference, and focusing on the role of the lab, role of laboratory professionals in fighting this pandemic. And so there were actually over about close to 3,000 attendees from 118 countries. And this was, of course, a virtual conference. Our first virtual conference held in February of 2021, but it turned out to be quite successful with speakers from 34 different countries, and this was actually quite successful. And also we had industry sessions, so there was a strong sort of collaboration to discuss some of the latest advances in diagnosing and monitoring the infection. I also want to mention some of the activities of IFCC. So IFCC's vision, as I already mentioned, is to try to directly support members around the world and try to directly impact patient care and public health. Not just have committee meetings after committee meetings without much impact on the real world. So the idea was to try to develop programs that can really assist societies around the world, but also populations around the world. So one of the programs, for example, developed is a global newborn screening task force. There are many parts of the world where newborn screening is not being done nationally, and I know Pakistan has some programs, but not a national program. This is the problem around the world. We actually, out of the world population, newborns, only about 30% are screened. 70% of newborns around the world are not being screened. So it's a huge problem. WHO and other groups are trying to make to support the new programs. And so IFCC has begun a program. We're actually already identified a couple of countries we're working with to try to establish new programs. And actually, Dr. Habib is a member of this committee, this task force, and we're hoping to also have programs here in Pakistan. Another program is to support labs in relation to quality. So we have a task force that's providing now free external quality assurance, EQA, to 10 countries. This program has already started as a pilot. 10 countries are supported in Asia, in Africa, and in Latin America, and actually a couple in Eastern Europe. So that program has started. We're also starting a program to try to create a global reference interval database. This database should be available in 1 or 2 years, and it would be a resource free to access, and it's hoping that all the students, trainees, lab professionals, scientists, physicians, even patients can go to this online resource and look at reference ranges for tests that they have done. So hopefully there will be a comprehensive database both for adults and children in the next couple of years. Also, we have started this global e-learning program. Some of you may have seen, I'm sure our chemical pathologist colleagues have seen our live webinar series. So we have begun this live webinar series, and actually I have a slide on that actually later, where we actually provide live webinars every 2 weeks. 3 speakers, 90-minute total, so short presentations, not very long, 20-minute presentations, 3 speakers, followed by 20 minutes of question and answers. And this has been working very well. We have actually had so far over 150 webinars in the last 2 years, and they've become an extremely good educational tool, especially for developing countries. And finally, we have started a task force on outcome studies. The idea is to demonstrate the value of laboratory medicine and pathology to the public, to the governmental institutions, to other healthcare professionals, even physicians who may not appreciate how important labs are. And so IFCC has started a program trying to improve that image or visibility. So I think that is sort of, so I wanted to, this is the live series, the webinar series I mentioned. So if you are not familiar, you could actually go to the ifcc.org and be able to register. You'll get future webinars, announcements. Every 2 weeks we have webinars, and we currently actually have surprisingly attendance from over 100 countries every 2 weeks with thousands of registrations. It's free to access and free to register, and then there is a certificate that is given at the end of the session. So it's become a good resource for many countries around the world. So it's a service that IFCC is now providing, and we use this special platform that is actually quite a well-established platform in the US and UK, and now being used for this international webinar series. Hundreds of speakers have already presented. So if colleagues from Pakistan want to, for example, present a webinar, it is possible. Another area I mentioned is visibility. IFCC is trying to improve visibility of our field, laboratory medicine and pathology, in the eye of the public, in the eye of the healthcare professionals, administrators, governments. And this is, but we want to do it through evidence. We want to show where we are making a difference. Why lab testing? Why pathologists and the service they provide? Why all of the testing that chemical pathologists and others provide are making a difference. And to do this, we're actually have a grant program where to support studies, and so far we have started this grant program. Already some groups have been funded to start studies. We also have developed this Global MedLab Week, which is basically a promotional campaign. It began this year. It began in April of 2022. It would be promoted every year in the future. The idea is to celebrate the vital role of lab medicine and lab professional in both public health and patient care. Well, as you know, during the pandemic, the public and the governments became much more aware of how important labs are, because without laboratory testing, public health programs cannot function. It's hard to have public health programs without detecting and diagnosing infections and monitoring public, transmission across various groups. So therefore, I think the pandemic actually has been an excellent opportunity to increase visibility. And so this program has started recently. Now, I'm almost done. Let me see. Yeah, so what I want to do is encourage you. Now, this is initiated in April of 2022, but there will be a new program this coming spring. So I want to encourage colleagues in Pakistan to be part of this. You could actually we can provide tools for you to promote your field of laboratory medicine and pathology, chemical pathology, histology, and other areas, anatomical pathology, and the importance of these areas to your own communities, to your own institutions. I want to also mention and this is for young scientists, that IFCC has programs specifically for young scientists. And I mentioned 2 young scientists from Pakistan were already supported this year. And these are scholarships that are available to fund attendance at a conference in Europe or somewhere else. So actually there were scholarships for people to go to Korea this year. We had a conference in Seoul, Korea. But we have a conference coming up. Professor Sergio Bernardini, who is here, is actually the president of the conference. It's going to be held in Rome, in Italy, in May. And there are scholarships available. We're going to be providing about 30 scholarships for developing countries only. And these are for young scientists under 40 years of age. So I want to encourage some of your young scientists to apply. Also, we have this exchange program. So some of young scientists can go to other countries for training between 1 and 3 months, paid for by IFCC. So there is a call already for nominations. We have already received close to 100 applications from around the world. We have been doing this for years, but we are expanding. So this professional exchange program has been going on for years, but we want to make it more visible so that communities like you in Pakistan are more aware of the program and can apply and benefit from it. We also have this task force on young scientists. So we have people from young scientists running this whole task force. So again, many new programs trying to support our young scientists, our new generation of scientists. Finally, I want to again mention that we have 2 major events coming up. So I want to encourage you to attend as much as possible. One is Roma next spring, in May of 23. Then the following year, actually, our conference comes closer to you here in Dubai. So if you cannot make it to Rome, please make sure you come to Dubai. These are very strong conferences with thousands of attendants, and we usually have hundreds of international speakers. So an excellent opportunity for you to participate in an international conference. So these conferences are held both in May of each year, May of 23, May of 24. But this will continue for every year. There is 1 year a conference in Europe, 1 year outside Europe. So it rotates through internationally. So I just want to, actually maybe I should just end here and thank you for attending, and I'm happy to answer any questions privately if you have any questions about IFCC. Thank you very much.
Thank you very much, Dr. Khosrow.
Now I'd request Professor Bushra Muiz to please come on the stage and introduce our next keynote speaker.
Assalamu alaikum and a very good evening. Indeed, it's my honor and privilege to introduce Professor Dr. Catherine Hayward. Professor Dr. Catherine Hayward is an MD, PhD, and clinical and laboratory hematologist who is a professor of pathology and molecular medicine at McMaster University and the head of coagulation for the Hamilton Regional Laboratory Medicine Program in Canada. Dr. Hayward is a global expert on the clinical and laboratory diagnostic evaluation of bleeding disorders. She is the immediate past president of 2 societies, Thrombosis Hemostasis Societies of North America, and the immediate past president of the International Society for Laboratory Hematology. As a clinical scientist, Dr. Hayward has received many honors and awards, including the Gold Medal Award from McMaster University and from Royal College of Physicians and Surgeons of Canada. Today, Dr. Catherine will enlighten us on the perspectives of unique quality assurance challenges faced by coagulation laboratory. Please welcome Professor Catherine Hayward.
It's my pleasure to be here, and I thank Bushra and other people involved in organizing this meeting for this wonderful invitation. So those of you who are afraid of coagulation, don't worry. I'm not going to get too specific about the complexities of blood coagulation, but want to talk about quality assurance and pick up on some points we've already heard tonight about importance of advances and thinking broadly and outside the laboratory and trying to make sure we add value to what our laboratory testing can provide to patients. I don't have any relevant disclosures. So the key components of quality assurance for medical or laboratories is that we have to have systemic efforts. We have to ensure that our lab services are meeting the clinical service needs and also expectations on performance, design, reliability, and maintainability. It involves absolutely everyone in the lab, including the physicians engaged in and overseeing the laboratory. In the last couple of years during the pandemic, we undertook a major refresh of our coagulation lab services, and I learned a lot during the process. I'm glad it came at this stage of my career, and it made me think about how deep the knowledge one obtains with years of laboratory practice, and how do we pass that on to other people. Locally, we're a center that is very famous for management of thrombotic disorders, bleeding disorders. We have some unique offerings. We support many labs in Canada who don't have as extensive a test menu, but we also have 24-hour, 7 days a week support of some very critical patient services with increased demands for coagulation testing for those individuals, such as patients coming in with acute stroke. Quality assurance also means addressing the demands for highly qualified physicians that are needed to run our laboratories. And at this stage in my career, some of the people I've looked up to have looked to me to help train some individuals that are going to be taking over the practice of individuals that I've admired that are retiring from practice over the next few years. So how do we tackle this? McMaster has gotten very formal about training fellows, so you can no longer do it informally. You have to create a competency-based training program. So part of what I did during the pandemic was create a couple of new programs to train our future coagulation experts. One that spans both clinical and laboratory services, and the other for hematopathologists that is focused in the laboratory. My department chair thought this was a wonderful time to create a chair of a fellowship committee for our department. And we now have 5 fellowship programs and are looking to create more in our department. So this actually made my job during the pandemic much more interesting. When we created these programs, we had people join them right away. So we're on to our 5th trainee, and we've got people that are already organized to start next year. So to ensure that our services meet clinical needs requires broad consultation, so we have to keep stepping out of the lab and interacting with other individuals. Coagulation serves both diagnostic purposes, but we also provide prognostic information and also adjust therapies for anticoagulation, factor replacements. We have at our center clients, our patients within our outpatient and inpatient environment, but we also have outside clients, patients whose samples are coming to us from afar. And we also have the important role of making sure that we're providing the appropriate services for both the patients with bleeding problems, thrombotic problems, and other service problems. We support the ICUs, cardiac surgery, perfusionists, anesthesia, ECMO patients. ECMO became a very big service during the COVID pandemic. We have major trauma centers, a regional stroke service, and others. So we had to network with all of these services to say, what's happening in your area? What are you seeing are the changes that you're going to need to coagulation lab services? And importantly, any change we happen to introduce in the lab related to things like monitoring unfractionated heparin, we have to coordinate that with other services, including the Hospital Order Set Committee, Medical Advisory Committee, the pharmacy. It's a pretty big team. So during the pandemic, we were on a project to replace all of our coagulation analyzers in a multi-site program. So Hamilton Health Sciences has 4 acute care sites. St. Joseph's Hospital has an inpatient and an outpatient site, and all of those sites are harmonized together on the same equipment and lots of reagents. So we were looking at updating pretty much everything that we do, and had to, for a project like this, involve a big team of core and special coag lab services, information technology, purchasing, management. And because of the size of the project, we had to go for a formal request for proposal process. So we were supported by project team, project leads, and after selecting a winning bid, we had to develop a big team for implementation. So this process of change management is always an important opportunity to align and improve services in other ways. And I was overjoyed to have fellows working with me so we could talk about these things rather than just talking to yourself. So we went through the standard RFP process with a team of more than 20 people, and everyone's vote counted equally. Except for there were some essentials that the information technology team scored to decide which solution would be appropriate. As part of getting ready for change, we wanted to be prepared, to be proactive, to be smart, not reinvent the wheel, not discover any problems that people had already found solutions before. So we, as part of our preparation, did some virtual visits and dialogues with other labs using the solutions we were looking at, and then the final solution that got picked in our RFP process. That was very helpful. So we went through a huge number of tasks, and having had to sign off on all of the validation data, it was a pretty big role. So this kind of summarizes the big to-do list of things that we had to finish up before going live. And we started early deciding that we would look at latest guidance, documents, and evidence to refresh the sort of interpretive comments we were also releasing with tests. So a lot of consultation, a lot of interaction. It was a very exciting time. So one big thing that we faced was a massive culture change in going from a lab that has always measured coagulation using an instrument with a mechanical clot endpoint detection to the optical way of detecting clots. And I show at the bottom of the slide a graph of optical clot detection showing the results for a PTT test. This was brand new to us, so individuals like myself had never really paid much attention to them, but we had to be ready to deal with them. And I think this is a wonderful opportunity for artificial intelligence to take over what we do eventually with clot curve analysis, but we're not there yet. So technologists, people on the bench, and people like myself needed to be able to deal with these abnormal clot curves, which we'd never had to deal with before. We did what was called by management the Big Bang Go Live. So that means every single site, every hospital involved in this, the pharmacy order sets, everything went live at the same time, same day, which was back in January of this year. As part of the plans to go live with this change to clot curves, I made the policy that if a technologist thought an abnormal clot curve might be due to a low fibrinogen, I gave them the authority to add on the test to make it lab orderable, and we let the clinical services know that we would be doing that. We had to carefully coordinate with pharmacy the change to heparin monitoring, so all of the existing order sets, and there were many more than I would have guessed there would be, in our hospitals had to go live at the same time that we went live with the new heparin therapeutic range, and pharmacy was prepared to support the nurses and physicians who had patients undergoing transition that day. We also, and I highlight at the bottom, warned people that we were moving to instruments that were going to do a pre-analytical sample quality check. Didn't think that would be a huge culture change, but it turned out to be. So the Big Bang happened. It was a good day. But some interesting thing happened that we weren't entirely anticipating. So one was this permission to add on a low fibrinogen to samples submitted without a fibrinogen order. We were identifying critically low fibrinogens in patients where a low fibrinogen was not suspected. So this is very interesting. It seems to be an advantage of doing clot curve analysis. As you may or may not know, low fibrinogens are emerging to be a prognostic indicator for patients at risk in a whole slew of medical diagnostic problems, from trauma to postpartum hemorrhage, head injury. The list is really quite large. So we think this is something of value, and one of our fellows is working on developing a formal QA project to look at how often this happens, what kind of patients. But I can tell you it's real. One thing I didn't anticipate, and it has generated a lot of correspondence, phone calls, some anger, and during a time when we're short-staffed in the hospital, we had started this pre-analytical check, and about 5 to 10% of all the coagulation samples sent down to our lab after go live were getting rejected for being underfilled. So angry calls from the wards. It's mainly nurses in our hospitals who are drawing samples, blaming the tubes, suggesting we pool 2 vacutainers to fill it up to the right volume, doesn't understand the issue that there's too much anticoagulant in that blood. And we also had to check to make sure that wards weren't using expired vacutainers. So that created major angst. The problem was lowest at the site where the lab collects a higher proportion of the inpatient services, and unlike nurses, our lab staffs have to demonstrate competency in blood collection. So why reject more than tubes that are less than 90% filled? We were pleading to turn down the level that was required. Well, there's several reasons to do it. Where we practice in Canada, it's a mandatory accreditation Canada requirement, so I'm sorry we can't change it, but there's actually good evidence, and this was reviewed in an article last year, that you can make medical errors that become significant in things like INR monitoring for doing blood coagulation testing on a tube that's just under 90% filled. So you have to. We double-checked our tubes. We were hearing that they thought they were wrong, and in the lab we used a syringe and a large bore needle to show that no, the vacutainers we had in the system were working perfectly. During the pandemic, there have been vacutainer shortages, so we looked at an alternate tube. It failed. So good thing we never introduced that tube. So what works to reduce a problem like this? One of the leaders at one of our sites, a manager who was studying an MBA during the pandemic, she did a study to show that if you have the lab staff draw samples, you get markedly less pre-analytical errors. That actually saves the hospital costs. But as the cost of collecting samples is currently paid for by the ward budgets for different services, there's not interest in transferring that money to the lab, so that didn't go anywhere. But it's something to think about. There is published evidence that education helps, but like everything that you try to do to improve that requires education, the effect after you do the education wears off, and it's never 100% effective. So if you have better solutions than education, let me know. We're doing follow-up actions, and this is an example of another memo that we've sent out alerting them that no, it's not the problem with the tubes, it's a problem with technique. And we have a lot of consultation going on between the people in our lab that know all about proper sample collection with the wards to try and help and support people to improve, to reduce this potential cause of medical error. It's annoying for patients to think that 10% of their coagulation blood draws are going to have to be drawn again. The other thing that I think is really important with quality assurance is when you make change, how do you communicate that out? And our lab program puts out a newsletter that's got pretty broad distribution, and we took the opportunity to highlight all the changes we'd made to coagulation testing in the newsletter. So I think as a leader in a laboratory, you have to think all the time about how you're going to make sure the clinical service is aware of what you do. And I engaged our fellows very much and our technical experts in preparing this feature article. So some highlights of the practice changes, we kind of itemized through everything that we had done so that they had an idea of some of the important details, things like changing to a protein C chromogenic assay from a clot-based one, so could account for some differences in patients tested before and now. But we decided to devote about 30% of the content of the newsletter to tips to clinicians, so to remind people of some important things. So these are examples of some of the tips that we put in, tried to keep them short, to the point, an important issue, and I think these are some things people that even cover the hematology service weren't necessarily aware of, that our screening tests of coagulation don't detect mild to moderate reductions in fibrinogen. So if you're worried about a patient maybe having a low fibrinogen, to order the test. So these are some general examples of tips. We also did quite extensive tips related to the changes we were putting in place to lupus anticoagulant testing. We really revamped the process, made the numbers that we got from the different screening and confirmed tests part of the report with an overall positive or negative. and then a big interpretation that included looking at the results of the screening tests of coagulation to look for coagulopathies. And I had my day made at last Friday's Grand Rounds when I asked people how this was working out, and I was told that people love it, that they're using the lupus anticoagulant interpretive comments as part of teaching learners about what affects the test results. So I think this was a big journey to make sure that we were fitting the needs of the clinical services, and to try and do it in the best way we could. So my final thoughts. Quality assurance is so important to our coagulation labs. It has to be a collaborative process involving our clinical partners. So dream it, believe it, achieve it, and then once you think you're there, work on improving it some more. And I'd like to end. It's a pleasure to be here on behalf of ISLH representing our organization. We've had years of wonderful collaborative interactions with people in the Pakistan Society for Hematology, and I'm very happy to be here at your pathology meeting. And I hope that many of you can join us, if not in person, virtually next year when we have our meeting in May. Thank you.
Thank you, Professor Catherine. We'll pause here for 2 minutes. Our chief guest, Dr. Atar Rahman, has asked for a leave, so I would request Dr. Shahid Parvez to please present a small gift to Dr. Atar. I would request both of you to come on the stage, please. Thank you. Thank you, Dr. Atar Rahman. Thank you very much.
We'll continue our session and move to our next keynote lecture. I'd request Professor Dr. Zara Hassan to please come on stage and introduce our next keynote speaker. It will be a live online session.
Assalamu alaikum and good evening. It gives me great pleasure to introduce Professor Caroline Kuchenbecker, who will give her lecture online on a very cutting-edge topic. It's the role of genetic epidemiology in global health and well-being. Professor Caroline Kuchenbecker is Professor of Genetic Epidemiology, Department of Mental Health Neuroscience, Division of Psychiatry at the University College London. She received her doctorate in 2014 from the University of Cambridge. Her research has focused on conducting studies to identify variants or genetic elements affecting traits. She was involved in several breakthrough discovery studies for cancer susceptibility loci and has also worked on different aspects of cancer risk prediction. Professor Kuchenbecker's research aims is to understand the patterns of how genetic traits influence complex traits. This involves questions as to how strong is the overall influence of genetics, how do disease subtypes differ in terms of genetic risk factors. Her current focus is to compare the genetic basis of traits across populations such as Africans and Europeans, using polygenic methods and to try and develop an inclusive approach to populating genomic databases that would provide more diversity. She has collaborations with research groups at the Wellcome Trust Sanger Institute, the University of Cambridge, UCL, and German Cancer Research Center. It's my honor to welcome Professor Caroline to give her talk.
Thank you so much. It's my great pleasure to be here today. And I'm really sorry that it will have to be online. I would much rather be there and network and talk to you all. Before I start, can I just confirm that you can see the slides and the sound is okay? I'm assuming it's a yes. I hope you would complain.
Yes.
But okay, fantastic. Thank you very much. Thanks a lot also for the lovely introduction. I'm here today with two different affiliation heads. So I have my role at UCL as an academic, and I'm also contributing to the implementation of genomics into healthcare in the United Kingdom as the scientific lead for diverse data for an organization called Genomics England. I will tell you a little bit more about it in a second. There we go. So let's start maybe with a little focus on England, just to show you what we are doing here. Genomics is actually not just a research area anymore. It's now a very real, practical, key part of our healthcare system. And the UK national healthcare system was actually the first, in England in particular, to offer whole genome sequencing as part of routine medical care. So in the UK, patients with rare diseases are virtually all eligible to get whole genome sequencing. And the same is true for a group of cancer. Originally, they started out as sort of combined research / clinical project with a 100,000 genomes project. And for that, Genomics England was actually established to implement and see this through. That project has now been completed and is now moved over, as I mentioned, into a routine healthcare system. And all patients that are currently undergoing whole genome sequencing are also asked to contribute to research and consent to be part of this large research data set. But that's only the beginning. We are currently expanding into other areas as well. So one of the very large projects in the UK at the moment is the newborn genome screening program. And we're planning to do whole genome sequencing on 100,000 newly born babies in the next few years. The idea here is to test and see how this information can be integrated into their healthcare and how it would benefit them throughout their lives at different stages of their medical treatments, for example, with respect to pharmacogenomics or picking up people of particularly high risk for different diseases. As you can see, so far sequencing was more focused on rare diseases and rare mutations, but this is expanding as well. And another very large project in the UK is the Our Future Health project, and that involves 5 million people who will not be sequenced, but will be genotyped on a DNA microarray, and will also receive some information back. And both of these are efforts really focusing on diverse groups in the United Kingdom. So in the future, this means it is very likely that genomics is also going to contribute to medical care related to complex common diseases. But genomic research so far does have a diversity problem. And these are some of the most up-to-date recent figures for this from our paper in Nature Medicine this year, where we looked at the number of papers for genome-wide association studies and different ancestry groups they included. And you can see here very clearly that the vast majority use data from people of European descent. And it's also actually, it's a little bit misleading because it sounds like all Europe is represented, but that's actually not true. It's probably not too hard to guess what are the countries that are largely contributing to this. That's the US, the UK, and interestingly Iceland, because they have a very big historic genomics program. People from South Asia or people of South Asian descent are particularly badly underrepresented, and that's especially true when we're considering the the large global population that people from South Asian countries are making up. Now, this has been pointed out as a problem actually already quite a few years ago. And what has surprised me looking at this data more recently is that it hasn't really improved. It's slightly depressing, and we'll talk about why this may be a problem. So the health burden globally obviously isn't equally distributed. And that's true even within countries such as England. So for example, if we look at people of different ethnicity within the UK, the risk of dying from COVID was immensely different. If we look at men only to begin with, the risk of dying from COVID for men identifying as black was more than 4 times higher than white men. And you can see very similar massive increases in risk for people of Bangladeshi or Pakistani descent. That's quite shocking. And these differences persist even when you account for differences in income and other similar factors. COVID has really brought this to the wider attention of people in England, but in fact, this is a very well-known pattern. It's quite specific to certain diseases, and it has a high impact because it also affects very common severe diseases. To give you another example, if we compare British South Asians, so people of including Pakistani descent, we know that they have a higher risk of coronary heart disease, type 2 diabetes, non-alcoholic fatty liver disease, and also multimorbidity, so having multiple diseases at the same time. And that is true even when you recruit people from very similar areas, for example, in East London, where we're assuming that their socioeconomic background is very similar. So I'm not necessarily saying that this is all due to genetic differences, but clearly the disease burden is very different, and it is extremely problematic if we're excluding those people with the highest disease burden systematically from our genetic research. What does it mean in practice? I think that's important to consider, given that we are now widely using genomics in our healthcare system. The key application of genomics at the moment is carrier screening, looking for people with rare high-impact mutations, such as BRCA1 or mutations leading to severe childhood onset diseases. And a carrier screening usually can have 3 potential outcomes. Either a clearly pathogenic variant in a disease-associated gene is identified, or all the variants the person has in this gene seem to be benign, and the result of the screening is likely negative, although it's always possible that there's an undiscovered gene or a variant that hasn't been annotated yet. But the third, and actually very common outcome, is that there's a variant of uncertain significance, meaning for the patient with a condition, in a disease-associated gene, we find a variant, but we're not entirely sure if that variant does anything to the protein and if it is actually pathogenic and explains the disease. These variants of uncertain significance are extremely problematic in practice. Essentially, they're completely frustrating the goals of genetic testing. I mean, the test is pretty useless at that point because there's no way of clinically acting upon the result. We don't know if that person should undergo prevention, should be further screened, if they should consider family planning. It's very difficult. And this uncertainty obviously causes anxiety in almost all patients and can sometimes lead to unnecessary medical interventions when it's unclear if those would actually have any positive impact. So the pretty shocking finding from a few years ago was that these variants of uncertain significance are a lot more frequent for people of non-European descent. This is an example, I believe, from the US in the paper that made a lot of noise around this and was very helpful. In this group, they were screening for cancer genes on a breast cancer gene panel. And if you look here at the proportion of patients who receive a result of VUS rather than, a pathogenic variant or a negative result, it's only 20, still many, but it's 23% in the white non-Hispanic group. It's 44% in the black group, and it is actually over 50% in the Asian group. So practically, that means that the benefits of genetic screening are already very unequally distributed, and there is a practical problem for a lot of patients of non-European ancestry. So in the very large 100,000 genomes project, we were keen to look at whether we have the same pattern now with a few more years of research discovery and variant annotation in the meantime, and also with a much larger group of different conditions we were looking at. And here you can see our analyst, Sam Tolman, who did these analyses. First of all, he assigned the patients in our large cohort into different ancestry groups. The vast majority have European ancestry, but the data set is actually enormously diverse. And we think this, in fact, includes one of the largest whole genome sequencing data sets for people of South Asian ancestry. So it's over 9,000 patients who are of South Asian ancestry. And we've done analytically something very similar to what the study for Curien et al. Did. We looked at variants that are candidates but haven't been clearly assigned as pathogenic. And we looked at whether patients from different ancestry groups get more or less of these variants relative to patients of European ancestry. And you can see on that plot on the right that patients of East Asian ancestry, North African ancestry, South Asian ancestry, and almost all of the other groups compared to European ancestry all have significantly more of these variants. So practically the same is happening in the UK. People of non-European ancestry are getting a lot more variants of uncertain significance. In addition, we realized that the specific number of variants they get fed back is often particularly large, which is clinically problematic in genetic counseling. If a genetic counselor maybe has one or two specific variants, it may well be that by looking at research papers or collaborating with a research group, it may be possible to resolve the variant and understand if it's pathogenic or not. But if a patient presents with 20 variants of uncertain significance, it's just not feasible within our healthcare system, and that is very often the case. I wanted to give you a slightly wider overview beyond the 100,000 genomes cohort, and also mention the genes and health data. But before I forget, it may be important to notice that the data from the 100,000 genomes cohort is actually available to all researchers globally, and we feel that it's not as widely used as it should be. Do look into joining one of the GSIP groups. All it takes is submitting a research proposal and getting approval to be part of the group to be able to access and analyze those data in case you have additional research questions. So Genes in Health is a unique, dedicated initiative in the UK focusing on people of Bangladeshi and Pakistani descent. And it started in a particular area in East London that is characterized by higher levels of deprivation and poverty, and also some rather unhealthy patterns in terms of a number of outcomes, including BMI, type 2 diabetes, and hypertension. And this is a fairly large project with 100,000 participants. the samples were, first of all genotyped, but a very large proportion is also sequenced now. And you can see they're actually comparatively young, so born in the mid-70s, but they have overall a relatively high BMI, and given the relatively young age, a pretty shockingly high proportion of type 2 diabetes. So what did we do with these data? We, in the first two large papers that have been published on this, one is dedicated to type 2 diabetes, and the other one, this one I'm showing you here, focuses on cardiometabolic outcomes as well as coronary artery disease. What we did is compute polygenic risk scores for these various outcomes and compare how these risk scores perform. And we did this in comparison to a fairly similar sample of European ancestry. So if we start in this plot on the right, you can see, for example, systolic and diastolic blood pressure on the right. Overall, the polygenic risk score isn't performing particularly well, but actually the difference between the European ancestry samples and the British, Pakistani, Bangladeshi samples is not significant, it's small. And the same is true for some of the lipids. We have HDL cholesterol and triglycerides. There is a bigger difference for LDL cholesterol, but we suspect that this may be related to a difficulty in adjusting for lipid-lowering medication. So we assume that, in theory, the score could perform better. However, when you look at BMI, you can see that there is actually a difference. The polygenic risk score still performs quite well in the British, Pakistani, Bangladeshi samples, but it is worse than it does in Europeans. And most importantly, unfortunately, the biggest difference we observe for our main outcome of interest, coronary artery disease. So all of these others are key risk factors for that we like to model, we'd like to predict as well, but eventually it's really outcomes you're most interested in, and sadly that's where we're losing most of our predictive performance. So it's important in the future to use large data sets such as Genes in Health and other resources to improve the discovery genes for these complex diseases, and eventually get better prediction for diverse groups in the UK and globally. And I just wanted at last to give you a little bit of our vision how we can improve diversity and give you a fairly concrete roadmap for sustainable genomic studies across the world. And if you're interested in that, you can read more about it in our review paper. So fundamentally, it will not be possible without significant stakeholder will, and that includes, obviously, funders, researchers, both in the West, but also in global countries such as Pakistan. It needs significant infrastructure that involves computing, biorepositories, laboratory equipment. And one of the key moves, for example, in genomics is to ensure that the genotyping and sequencing is actually also done more globally in different countries. Strategic funding is absolutely fundamentally important, and within the UK has actually become more challenging with cuts to global development funds, for example. What it would really need is actually dedicated funds for international investigators and international collaborations to strengthen global research. I think one of the key requirements is capacity building, and with the immense number of very talented people globally, it's an absolute necessity to train people well, provide access to analytic strategies, and share knowledge and expertise on all levels of biomedical research. And eventually we need to work together in global consortia to make the most of data and knowledge sharing. And I just wanted to give you an example from my personal work, and this is now my UCL hat on rather than my Genomics England hat on. I would like to introduce you to the PAP study, which is the Pakistan Alliance on Genetic Risk Factors for Health, and it's probably the largest genetic effort in Pakistan right now. So together with Professor Mohammed Dayoub and Jim Knowles, as well as Dr. Aslan Hassan, we're recruiting 10,000 patients with major depression, 10,000 patients with schizophrenia, and another 10,000 patients with bipolar disorder from clinics across lots of different sites in Pakistan, as well as 15,000 controls, and we're genotyping or sequencing all of these patients. As this is funded by the NIH in the US and the European Research Council, and hopefully will be a fantastic resource, we're keen to collaborate with researchers internationally, particularly in Pakistan, of course. And this will be a wonderful resource to understand gene-environment interactions, the impact of consanguinity, increased diversity, and we're also keen to do capacity building, for example, training PhD students here in the UK and sharing the knowledge on both ends, and equally us learning from all of the efforts on the ground with the recruitment about depression and the other disorders from the patients. So that's the end of my talk. I would really like to thank the Genomics England Diverse Data team, in particular Maxine McIntosh, who is the overall lead for this program. The Diverge team, that's part of the PARC study I just mentioned. If you want to read more about it, here's the website, or get involved, get in touch with us. And of course, the Genes and Health team as well. Thank you all very much. It's been a great pleasure to be here.
Thank you, Professor Curley. We'd move to our next talk, and for that I'll invite Dr. Sabiha Anis to please come and introduce our next speaker.
I need the slide. Assalamu alaikum and a very good evening. I'm really honored and privileged to introduce Dr. Surena Kiani Ali Khan. Dr. Surena Kiani is a consultant immunologist at Bath Health NHS Trust. He's a consultant immunologist at Bath Health NHS Trust, where he has been the principal investigator of several international clinical studies on immunodeficiency diseases and hereditary angioedema. He studied medicine and immunology as part of the MB PhD program at University College London, UK. He did his PhD in immunology, studying the pathogen-associated molecular patterns effect of non-coding DNA sequences in vaccines on dendritic cell stimulation and maturation. He completed his postgraduate medical education specializing in allergy and clinical immunology at King's College London. Currently, he is moving to the immunology department at Royal Free Hospital, where he is working on the clinical trials on rare conditions including immunodeficiency and autoinflammatory diseases. Today he is going to talk about the vaccine response in the diagnosis of antibody deficiency.
Hello and good afternoon to my colleagues in Pakistani Association of Pathologists. Thank you very much for inviting me to speak in your very interesting conference. I'm sorry I couldn't make it in person to Pakistan, but it's one of my dreams that one day I come and visit, and I hope there'll be other opportunities. I'm Surena Kiani, consultant immunologist from Bath Health NHS Trust. and I do my academic work at Queen Mary's University of London. I'm there for another 2 weeks, then I'll be moving to Royal Free Hospital Immunology Department and University College London. Today, I'm going to talk about classification and signs and symptoms of immunodeficiencies, and then I follow this for the rest of my talk mainly to talk about antibody deficiencies, which are the most common forms of immunodeficiencies. I'll talk about how we investigate them, the use of polysaccharide vaccination as a way of investigating or diagnosing these immunodeficiencies, and then I've finished the talk by talking about some new tests that may be used in future for diagnosis of immunodeficiencies. So the immune system was designed to protect us against infections. So it was designed to fight infections mainly. In order to recognize pathogens, it does need to also recognize self and not harm self. And whenever you have an immune response, you have an expansion in the number of immune cells and mediators. And once the immune response is over, when the pathogen has been removed, they need to go back down to their original numbers. As a result of that, homeostasis is a very important feature of the immune system as well. And the other part of the immune system or feature of the immune system is immune surveillance, which until 10, 15 years ago, it was not quite clear whether this existed, but now there's very obvious evidence that the immune system is also designed to seek cancer cells and eliminate them. And it's not always successful, but that's part of the design of the immune system, and it's called immune surveillance. When the immune system breaks down, you have primary or secondary immunodeficiency, you can develop infections, you can develop autoimmunity, and this autoimmunity could be in the form of, for example, cytopenias or organ-specific autoimmunity, or it could be a form of against connective tissue. And by autoimmunity specifically, we mean it's directed against a particular antigen. As a result of the breakdown of homeostasis, we can have immune dysregulation, and immune dysregulation can have very similar effects to autoimmunity and cause autoimmune organ damage or autoimmune organ inflammation, but it's not against a specific antigen. It's just as a result of breakdown of homeostasis of the immune system. We have very specific diseases, for example, non-regenerative nodular hyperplasia, which happen in liver, in autoimmune or the lungs, and you have glial granulomatous lymphocytic infiltration of the lung, which can happen in antibody deficiencies such as common variable immunodeficiency or CVID. And as a result of breakdown of the immune system, we can also have an increased number of cancers, which is something very well understood. Also, because of breakdown of immune homeostasis and increasing in dysregulation, it can happen, particularly lymphoproliferative cancers. Immune deficiencies can be divided basically into primary and secondary, inherited and acquired. European Society of Immunodeficiency have released this for general practitioners as a way of remembering or being vigilant for patients who have severe, persistent, unusual or recurrent infections, and that should really warn them that there could be an immunodeficiency here. So the acronym SPARE. This is based on expert opinion, but the same factors were also seen when in a study which was done by a pediatric group in Manchester by Peter Arkwright. And they also saw recurrent infections, unusual infections, but also they saw family history is really important. If there's a family history of immunodeficiency, then the likelihood is higher. If there has been intravenous antibiotic use in childhood also is another sign, and also failure to thrive. This is a new paper, relatively new, 2021, which is a review, but also study of all the publications from immunodeficiency societies in different parts of the globe from every continent. I recommend this paper because it has got basically they've had a look at real evidence. So what were the increased infections in patients who were diagnosed later by immunologists as immunodeficient? And in general, these are the infections that they suggest should warn you against. Should warn you to be vigilant about the possibility of immunodeficiency. In this paper, they also have, for example, signs and symptoms that dermatologists should look out for, or signs and symptoms, for example, hematologists or respiratory physicians should look out for. So I recommend that paper. But in this paper, they looked at all the immunodeficiencies reported around the globe and showed, and this was something was known, but they actually showed evidence for the fact that there are basically antibody deficiencies are the most common forms of immunodeficiency, and they constitute about 55% of the cases of immunodeficiency. Immunodeficiencies on the whole are very rare and occur in about 1 in 10,000, but there's also an argument by this paper that they may not be as rare as we once thought. How do we diagnose immunodeficiency? So we know how do we diagnose antibody deficiencies, the most common forms of immunodeficiencies? We know that patients with antibody deficiencies have increased cytopulmonary infections, and every criteria used by different organizations state that you need to have a history or good history of cytopulmonary infections. And when you look, really, it's very difficult to obtain that kind of history by looking at patients' records. And patients might not give you the correct history. You might not have radiological evidence of lower respiratory tract infections, for example, which are more significant. So we need more, we gather this sort of history and try to gather this kind of evidence, but we need more objective evidence. So if we look at B cells, when B cells encounter antigen, if you look on the top left-hand side, there are two ways for B cells to produce antibodies. One is direct interaction of surface receptor of B cells, which is surface IgM, with long molecules which have repetitive motifs, such as polysaccharides. Then they produce antibodies which are usually in IgM form, and very little class switching happens and very little somatic hypermutation. So these are loosely binding, not highly specific, and are produced by short-lived plasma cells. But because IgM is pentameric, they have high avidity rather than high affinity. The other way for B cells to produce antibodies is via germinal centers. As a result of interaction with T cells, antigen is brought in by antigen-presenting cells, or such as dendritic cells, and with the help of usually T helper follicular cells, presented to the B cells class switch, produce mainly class switch antibodies by long-lived memory cells, and they undergo many rounds of somatic hypermutation. Therefore, they produce highly specific antibodies against that particular antigen. Now, the fact that these are more specific than these ones, than the IgM ones, doesn't mean these are better than those. They have different functions. These are able to cope with antigenic variations as a result of pathogenic changes, pathogenic mutations, whereas these are less capable of doing that, but they're much quicker and more specific. So what sorts of assays do we use to test B cells? One is we use serum immunoglobulin levels. We measure immunoglobulins. We also look at serum's specific antibody levels. So specific, mainly we look at streptococcal pneumonia, Haemophilus influenza B, and tetanus toxoid. Strep pneumonia, Haemophilus influenza, and other encapsulated bacteria are the main causes of cytopulmonary infections in patients with antibody deficiencies. We can also use flow cytometry for measurement of B cell numbers, and also we could use flow cytometry for looking at B cell phenotypes, which I'll briefly refer to later. There are usually two patterns when we investigate people for antibody deficiencies. Either you find severe hypergammaglobulinemia with low or absent B cell numbers, and the most common disease, which is a very rare disease, is X-linked agammaglobulinemia or Bruton kinase agammaglobulinemia. There are autosomal recessive forms, which are even rarer, that can have the same sort of pattern. The other pattern, which is more common, we find there are reduction in isotypes, immunoglobulin isotype G, A, or M. Mainly G really is the most important one, more than 2 standard deviation, and with normal or slightly reduced B cell numbers. So this is the second pattern, which is mainly found in a condition, common variable immunodeficiency. Common variable immunodeficiency is the most common form of antibody deficiency, found in 1 in 25,000 to 1 in 50,000, depending on the studies you look at, mainly present in adult life. And basically there's reduction in IgG plus one other isotype. They can have a variable degree of T cell deficiency, these patients. That's why it's called common variable immunodeficiency. So it's not just sinopulmonary infections. They might end up having ITP, autoimmune hemolytic anemias, or they can have, as I mentioned earlier, dysregulation and lung disease, liver disease, and various other issues such as granulomas. So this is a spectrum of diseases that by criteria can be diagnosed as having common variable immunodeficiency. But nowadays, we test everyone in our center, at least, or in many places in the UK. When you diagnose somebody with common variable immunodeficiency, you test them to see whether you can find a genetic by whole genome sequence and see whether you find a putative gene which might be causing this problem. And so far we know about 10% of these people in our service, for example, we know the causative gene for them. And if the genes, for example, ICOS, CD19 or LRBA or TACI, these are the genes which have been so far discovered and been shown to cause B-cell deficiencies and CVID. And this is not B-cell deficiency in numbers because most of these people have normal B-cells. So the diagnostic criteria for CVID, the 2 most important diagnostic criteria, one is the revised ECID criteria 2014, which requires low IgG and IgA, with or without IgM. So it's not important whether IgM is low or not. Whereas the ICON criteria, which is a bigger criteria produced by a larger number of people and involved immunology societies from across the globe, requires low IgG with one other isotype. So it doesn't matter whether it's IgA or IgM, it wants low IgG plus one of those. In the ICON criteria, low vaccine responses are also required, whereas the difference of that with the ECID criteria is that in ECID, either low vaccine responses or low switched memory B cells, which is part of the immune phenotyping that I mentioned earlier that we do on these patients. Now, in the ICON criteria, it requires that all patients are vaccinated for diagnosis and look at the vaccine responses, unless they have very low IgG, so there's no point looking at their vaccine responses. So antibody responses to immunization is something that we do when we are diagnosing patients. We want to diagnose patients with antibody deficiencies. Patients that fail to respond to polysaccharide vaccines, which is basically looks at B cells without the help of T cells. So T-independent antibody responses could be either patients with CVID or selective IgA. Some selective IgA deficiency patients, very few of them, because majority just don't have any immunodeficiency, they just don't have any IgA. Or conditions such as, for example, asplenia, or being young, less than 2 years of age. So children under 2 years don't respond to polysaccharide vaccinations and more susceptible to pulmonary infections with polysaccharide, with encapsulated bacteria. So are elderly. So this is, as I said, this is what we do here is we vaccinate with polysaccharide antigens such as pneumovax or Typhim, and we'll discuss that in a minute, and we're looking at this response here. So how do we know that actually these responses, these polysaccharide responses, are important for protection against encapsulated bacteria? This group in 2003 showed evidence for that by looking at patients who are susceptible to infection by encapsulated bacteria. And those are patients with splenectomized patients or infants and also patients with CVID. They looked at B cell in these patients, and they found that basically this is just normal control. They use CD22 as a marker of B cells, CD27 as a marker of memory, and you can see two distinct memory phenotypes. One are IgM memory, which we talked about earlier, which T-independent, as a result, T-independent responses, and more switch memory B cells, which are T-dependent responses. So they showed that in patients who were splenectomized, memory B cells all went down, but IgM memory B cells went down much further than switched memory B cells. They also showed that over a period of time, patients with splenectomy had reconstituted switched memory B cells, which are here, but they were not able to reconstitute IgM memory B cells. So where are these IgM memory B cells? They reside in the marginal zone of a spleen or marginal zone B cells, MZBs. Other evidence that they showed was that we know IgM actually reaches adult levels by the age of 2. They looked at antipneumococcal IgM, which reached adult levels also by the age of 2. And we know below the age of 2, these children are susceptible to infection with, for example, pneumococcus. They also demonstrated that over a period of time, the IgM memory B cells are not reconstituted in splenectomized or asplenic patients, whereas they are reconstituted in normal controls. They finally looked at a few patients with common variable immunodeficiency and showed or noticed, because this is not statistically significant, that patients with CVID who do have a lot of infections have undetectable IgM memory B cells. So this was the preliminary evidence showing that these marginal zone B cells in the spleen are responsible for protection against encapsulated bacterial infections of the lung. So we lose these in splenectomy, we lose them in antibody deficiencies. So these are some of these conditions which I mentioned earlier, where we don't have these cells. So in order to test people whether they have these T-independent antibody responses, we used polysaccharide antigen Pneumovax. Pneumovax has 23 serotypes of pneumococcal inside, and it's only purely polysaccharide. But the problem started when the conjugated vaccine, which in some ways is a much stronger vaccine, or there's more response to this vaccine because of the conjugated protein in there, which incidentally is tetanus toxoid. The conjugated vaccine has been given now in many countries in the world to children and some adults. And as a result of that, when we want to test these people, if they've had a previous history of having had Prevnar, we are not testing their T-independent antibody responses for these 13 serotypes. We are testing a memory response to T-dependent antibody production in the past. Now, some people argued initially, well, we could look at the 10 serotypes which do not exist in Pneumovax, and I beg your pardon, do exist in Pneumovax, but not represented in Prevnar. So this group had a look at that from Belgium, but they found that actually, to cut a long story short, those 10 serotypes were also affected. If you were vaccinated with Prevnar in the past, when you boosted with Pneumovax, all the serotypes were boosted to different degrees, but all serotypes boosted. This group, again, Peter Arkwright from Manchester, had an interesting observation. They looked, this is something which was suspected, but they actually demonstrated in 145 patients or children that IgG1 anti-pneumococcal responses are exclusively produced when you use Prevnar, whereas IgG2 is produced as a result of the polysaccharide vaccine or natural infection. So this is a way forward maybe to measure responses when you vaccinate, to see whether these responses are from just a B cell, pure B cell response, or whether it's a T helper involvement. However, We haven't really formalized this, and we're not using it at the moment. Nobody's studied to see how much the response should be when you're looking at IgG 1 or 2. So the thing we use at the moment is serotype-specific pneumococcal responses, and we basically follow in the UK the guidelines or WHO, which states that you need to have 70% of the tested serotypes need to be more than 0.35 microgram per milliliter. Here you can see a cutoff of 1.3. This is the cutoff which is used by immunologists in the United States. So the difference is huge. In the United States, they use a cutoff of 1.3, so there are more people who might be diagnosed with antibody deficiencies than in the UK. This is probably not based on good evidence what they do in the United States, because the measurements which set a cutoff of 1.3 were used a very sensitive immunoassay, which are no longer used. The WHO guidelines, or the WHO recommendation, used the ELISA and found 0.35. But we don't even use ELISA any longer, so we don't really know what should the cutoff be, but we know at least it's closer. What we use now is multiplex assay, so the cutoff we use in the UK and many countries is 0.35, and we go for 70% should be above of the serotypes tested. We normally test 13 serotypes, so about 8 or 9 should be positive. Now, there's a problem with that, and that's what is your baseline. If your baseline is 6, then you can reach 8 more easily than if your baseline is 1. So to use this sort of dichotomous measurement is not really accurate, and there are other ways probably to look at it. And this group recently wrote an interesting paper. They looked at using Z-scores to look at a continuous variable rather than looking at dichotomous, and that's maybe one way forward for measuring these responses. So in the past, people have talked about using natural antibody responses, and natural antibodies are, for example, antibodies against blood groups ABO. Blood groups ABO are also polysaccharides, and some people in the past used them and diagnosed people with or without them. This group in Belgium and Paris, they went and had a look at a cohort of their patients, a good number for immunodeficiency. You don't get many people, 180 Caucasians, and they looked at them, and out of these people, 10% of those people had failed to respond to pneumovax. So they used that as gold standard. And they showed that actually the ROC curves for using natural antibodies was as good as tossing a coin. So really, this is not a good way of measuring polysaccharide responses. In the practice parameters, United States practice parameter, the latest one, which was 2012, they suggested that Salmonella typhi could be used also for vaccination. Now, there was a paper in 2003 from Oxford group, Siraj Misbah, Helen Chappell, and Mani Ferry. They had a look, they developed a reproducible ELISA, and they look at baseline levels, and they showed in the population, they looked at blood donors, the baseline levels of Salmonella typhi antibodies were low, and so therefore, maybe this is a good, we can measure Salmonella typhi levels. Nothing happened after that. There were no publications. We wrote a review on, probable use of Salmonella typhi, and this was a review of literature, really, probable use of Salmonella typhi as measurement of adaptive immunity or B-cell responses in 2016. And then later on in, I think it was 2018 or 2019, a paper came out which used polysaccharide vaccine using Typhim or Typhim V vaccine as a way of measuring polysaccharide responses in patients with humoral immunodeficiency, patients with hematological malignancies who were suspected of having antibody deficiencies. They saw that in this population, the baseline levels much lower for patients with hematological malignancies. Baseline levels for Typhim were lower than pneumovax, which is what you want when you want to vaccinate people and see responses. And they showed that the ROC curves was much better for Typhim, which is the green line, than for pneumococcus, and with high sensitivity and specificity. They also showed a correlation with clinical picture, presence of bronchiectasis and other infections such as zoster, and also they showed that patients who didn't respond to Typhim had more severe lower respiratory tract infections, for example. They compared the two vaccinations, pneumovax or Typhim, but they couldn't really find a connection between, they couldn't correlate responses to one vaccine to the other one, or lack of response to the vaccine. And we also had a look at our cohort of patients over a number of years. We didn't see a correlation, but what we found was something you would expect. The elderly responded poorly to polysaccharide vaccine with pneumovax, and also they responded poorly to Typhim. We had a look at a cohort of 58 children who were referred to our pediatric department with recurrent severe unusual infections or had a family history of immunodeficiency. We vaccinated them with Typhim because they all had received Prevnar in the past and we couldn't really use that. We found 20% of these patients, 11 out of 56, had a poor response, less than 5-fold to Typhim. These patients who were poor responders to Typhim, there was basically a degree of correlation between low IgG and that, and also low CD3 T cells. But this was not statistically significant in this small group of people. But something which was statistically significant was that all these patients after 1 year were diagnosed with primary deficiency by genetics or by other means. So it was a very good predictor of these patients having primary immunodeficiency, and this is the different types of immunodeficiency diagnosed in these patients. So I'm going back to IgM memory, and this is the final part of my talk about future. I'm bringing this up because we talked about IgM memory B cells were very important in protection against encapsulated bacteria. They also, in this group, Italian group, showed basically that in their common variable immunodeficiency patients, they divide them into 3 groups. One group have lower respiratory tract infection with basically continuously, despite the fact that they were on prophylactic antibiotics and immunoglobulins, they also had CT evidence of end organ damage, such as bronchiectasis. The second group didn't have any of those and doing well on immunoglobulin replacement, and the third group was somewhere in between. And they showed basically that switch memory B cells were present in group 2 who were protected, but not in group 1. I mean, all memory B cells were low because they all had CVID, but switch memory unswitched memory or IgM memory was actually protected in these patients in group 2. They also saw that was reflected in the level of pneumococcal antibodies in these patients, and hence this is something maybe we could use in future. We found further evidence for that in a study we did of the UK Registry for Immunodeficiencies, which is about 5,000 patients. Nowadays it was 4,086 in 2016. And what we found in patients who were all on immunoglobulins had antibody deficiencies, which basically demonstrated that patients who had low IgM and IgA at the time of diagnosis were predicted to develop bronchiectasis and have more antibiotics later. A single center study in the UK from Royal Free also demonstrated that in 110 patients later, a couple of years later, and they showed that IgM was a predictor. This is a study from Freiburg in 2007, and they vaccinated patients who were on immunoglobulin, and they used a very complicated formula to work out how was the response to that vaccine, because they were already on immunoglobulin replacement. So they managed to find a way of actually teasing out what is the response to the vaccine, despite the fact they're receiving immunoglobulin replacement therapy. And they also looked at their B-cell phenotype, which I talked about previously. So patients with CVID can have different B-cell phenotypes. Some have low switch memory, some have increased transitional cells, some have absence of IgM memory, and we use that for prognostic reasons. But in these patients, what they showed that patients to be able to respond to vaccines, they needed to have IgM memory B cell. It was absolutely necessary. It wasn't sufficient, so you needed other things probably, but IgM memory B cells are sufficient. So basically, on the whole, maybe it's a good idea to develop assays or look at patients' IgM memory B cells as a way of diagnosing whether they have antibody deficiencies or whether they will develop antibody deficiencies. I mean, you may say, so why don't you just measure the immunoglobulin? If the levels are low, you say you have antibody deficiency, but that's not the case. Antibody deficiency patients, there are patients, I've got so many patients who've got IgG of 4, or 4.5 or 3.5, which is lower than normal, but they don't develop infections. And we don't know what the reason for that is. Probably switched memory B cells. They've got good switched memory and unswitched, I beg your pardon, they've got a lot of IgM memory B cells. So this is another very interesting assay which was developed by the Freiburg group, and it's not gone any further. There's just one paper they wrote on it, maybe looking in B cell, stimulating your B cells in vitro and looking to see whether you produce proper responses or not. That might be one of the future assays we use. The thing which is I'm very interested in, developed by somebody called Deborah Dunn-Water, so if you see, this is an antibody diagrammatically, an antigen, the part of antigen which binds the antibody called an epitope, the part of the antibody which binds the antigen is a paratope. So the paratope of an antibody is coded by CDR3 in the genome, and CDR3 spectrotyping is a way of looking at the diversity of CDR3 region. When you can vaccinate people, and Deborah Dunn-Water has done that, you vaccinate people, then you look at the diversity of the CDR3 generated, the paratope generated, and she's shown that this diversity is reduced with age. And therefore, there's an impairment of diversity in patients who have antibody deficiencies. And it would be very interesting if this could be developed as a way of diagnosing patients with immunodeficiency. So with that, I finish my talk, and thank you for listening. And if there are any chances of answering questions later, I'll be at your service. Thank you.
Thank you very much, Dr. Sorani. And this would be the last keynote talk for the session. Thank you for your careful listening. Now we'll be presenting small gifts to the society presidents in following order. I would request Dr. Shahid Parvez and Dr. Adnan Zubairi to come on the stage to give the gifts. I would request President Pakistan Society of Chemical Pathology, Major General Retired Syed Raza Jafar, to come on the stage. Thank you.
Of appreciation and hope that this unity continues, and we already announced the date of next PAP conference, that is 17, 18, 19 at PC Lahore. So a very small token of appreciation.
Thank you very much. Thank you.
Thank you.
Thank you.
I would request Dr. Naila Kiani to come on the stage, President, Histopathology and Cytopathology Society of Pakistan. I would now request Dr. Bushra Muiz to come on the stage on behalf of the President of Society of Hematology. Thank you.
So on behalf, all right. Yeah, I know. Indeed, Dr. Bushra Muiz did most of the work, as in the organizing committee, for this hematology program. So, but as this one, at this time, at this very time point, it's for President, so thank you.
I would now request Dr. Faisal Hanif, Secretary, Society of Microbiology, to come on the stage. If he's not around, then I would request Brigadier Gohar Zaman to come on the stage and take the gift. Brigadier Gohar Zaman. Okay. I'll move to the next gift. Secretary Professor Sabiha Anis, on behalf of President of Pakistan Society of Immunology. Please come on the stage. Thank you.
Thank you. Dr. Savia. So again, I think Dr. Savia did a marvelous, and this time indeed the relatively smaller and newer societies, immunology is not that new, but immunology and molecular pathology, they were highly forthcoming and proactive.
Next, I would request Dr. Zahra Hassan, President, Pakistan Society of Molecular Pathology, to come on the stage. Thank you.
It's heavy.
Thank you, Dr. Shahid and Dr. Adnan.
Thank you.
Thank you very much. I would now request Dr. Professor Ikramuddin Ujjan, Secretary PAP and Vice Chancellor, Lakat, University of Medical Sciences, to come on the stage and give vote of thanks. Thank you, Dr. Ujjan.
Bismillah ar-Rahman Rahim. Respected Professor Shahid Parvez, President Pakistan Association of Pathologists, Professor Adnan Zubairi, Secretary Organizing Committee, and Senior Professors of Pathology, faculty members, dear students, and representatives from the media and from the diagnostic companies. Assalamu alaikum and good evening to everyone. On behalf of Pathology, Pakistan Association of Pathology, I am highly thankful to all the participants who are presenting their research in the form of oral presentation or posters, and I am also grateful to the organizers, honorable speakers, and the panelists for their time and energy for investing for organization of this program. I am also grateful to our industry partners for their generous support for the Congress. We encourage you to visit exhibition hall, learn about the latest diagnostic and therapeutic advances available to us, and exchange ideas with representatives from the diagnostic and pharmaceutical industry. So I am highly thankful to all the participants. So thank you very much, sir.
Thank you, Professor Ujjan. With this, we'll conclude the inaugural session. I would request all the guests and participants to go to the exhibition hall and followed by dinner. Thank you.
Thank you very much. Enjoy the dinner.